If you like the space and learn about its curiosities, consider subscribing to the channel. Thank you for your attention and enjoy the video. In the realm of human curiosity, few questions resonate as deeply as the origin of the universe. To think of the universe's beginning is to embark on a journey through space and time, exploring the realms of cosmology, physics, and quantum mysteries. The Big Bang Theory stands as one of the most profound and extensively studied explanations for how our universe came to be, setting off a series of events that would lead to the formation of galaxies, stars, planets, and ultimately life as we know it. Imagine a time when there was no time, a moment before moments existed. According to the Big Bang Theory, everything began about 13.8 billion years ago, in an event unlike anything we could ever witness today. This wasn't an explosion in the conventional sense, but an expansion, a rapid outpouring of energy and matter that would evolve into everything we see around us. At that moment, all matter and energy were compressed into an infinitely dense and hot singularity. The conditions were so extreme that conventional physics breaks down. Temperatures and pressures were unimaginable. This singularity then began to expand, transforming into a vast, continuously growing universe. One of the most intriguing aspects of the Big Bang is how it challenges our understanding of nothingness. In the seconds following this monumental expansion, fundamental particles emerged, creating a universe that was still unrecognizable. Protons, neutrons, and electrons, the building blocks of matter, started to form, governed by the intense forces of physics. For the next 380,000 years, this primordial soup remained opaque, as particles collided incessantly in the heat of the newborn cosmos. When the universe finally cooled enough for atoms to form, photons began to travel freely, giving birth to the cosmic microwave background, CMB. This faint glow of ancient light still permeates the universe today, serving as a snapshot of its infancy. The CMB is the oldest light we can observe, a relic of the first observable moments after the Big Bang, providing invaluable insight into the universe's early stages. Astrophysicists study this ancient light meticulously, revealing a cosmic baby photo that has been traveling through space for nearly 14 billion years. Yet, the Big Bang Theory also raises questions that physicists continue to investigate. What, if anything, existed before the Big Bang? Could there have been a previous universe? Or was this truly the beginning of all space and time? Some theories suggest that our universe could be part of a multiverse, a collection of potentially infinite universes, each with different laws of physics and histories. If such a multiverse exists, it would profoundly alter our understanding of existence itself, suggesting that our universe might be just one bubble in a vast cosmic ocean. The inflationary model is one extension of the Big Bang Theory, suggesting that in the first fractions of a second, the universe expanded exponentially faster than the speed of light. This rapid inflation smoothed out irregularities, creating a uniform universe. This idea explains why the universe appears largely homogeneous and isotropic, with similar properties in all directions. Inflation also provides insight into the formation of galaxies, as tiny quantum fluctuations during this phase would later expand to become the large structures we observe. Gravity played a crucial role in shaping the universe after the Big Bang. As the universe expanded and cooled, matter began to coalesce under the influence of gravity, forming vast clouds of hydrogen and helium. These clouds collapsed to form the first stars, which were massive and short-lived, ending in spectacular supernova explosions. These supernovae scattered heavier elements throughout the cosmos, seeding the formation of subsequent stars, planets, and ultimately life itself. The elements that make up our bodies, carbon, oxygen, nitrogen, were forged in the hearts of ancient stars that lived and died billions of years ago. Dark matter and dark energy are two components of the universe that further deepen the mystery of the Big Bang. Though we can't observe dark matter directly, its gravitational effects on galaxies and galaxy clusters provide clues to its existence. It forms a sort of cosmic scaffolding, shaping the universe's structure on large scales. Dark energy, on the other hand, is even more elusive. It's thought to be responsible for the accelerated expansion of the universe, driving galaxies apart at an ever-increasing rate. These two components make up about 95% of the universe, leaving us with the challenge of understanding a universe where the observable, familiar matter comprises only a small fraction. Some scientists propose that the Big Bang may not have been a singular event, but rather one in a series of cosmic cycles. This theory, called the cyclic model, suggests that the universe might expand, contract, and rebirth repeatedly. In this model, the end of one universe could lead to the beginning of another in a perpetual cycle of cosmic regeneration. This idea resonates with ancient philosophical concepts, yet it remains highly speculative, awaiting more evidence. As we observe distant galaxies and cosmic structures, we are effectively looking back in time, witnessing the universe as it was billions of years ago. This cosmic archaeology allows astronomers to piece together the story of the universe's evolution from its infancy to its current state. Advances in telescope technology, such as the James Webb Space Telescope, allow us to peer even deeper into the cosmos, offering unprecedented views of the early universe and testing our theories of cosmic origins. The Big Bang Theory has not only redefined our understanding of the universe's birth, but also our place within it. It suggests that the universe operates under natural laws, giving rise to complexity and life without the need for supernatural intervention. For many, this raises profound philosophical questions. If the universe began in a random burst of energy, what does this mean for the meaning of life and humanity's place in the cosmos? The study of the universe's origin also forces us to confront the limitations of human understanding. While we have developed models to describe the events following the Big Bang, the question of why remains elusive. Why did the Big Bang happen at all? What caused this cosmic ignition? Some scientists turn to quantum mechanics for answers, exploring the idea that the universe could have emerged from a quantum fluctuation. Others propose that the universe is a self-contained entity with no external cause or reason. This concept challenges our intuition, as we are accustomed to a world where every effect has a cause. In the grand tapestry of existence, the Big Bang Theory stands as a testament to human curiosity and ingenuity. It represents our relentless quest to understand the universe, to reach beyond the stars and grasp the forces that shape reality. As our tools and knowledge grow, we may come closer to answering the mysteries of the Big Bang. Yet, each discovery often raises new questions, suggesting that the universe's story may be far more intricate than we ever imagined. The exploration of the Big Bang is not just a scientific endeavor, it's a profound journey of existential reflection. Every star we observe, every galaxy we study, echoes the birth of the universe. Each of us is a part of this cosmic story, composed of stardust forged in the hearts of ancient stars, bound by the same physical laws that govern the galaxies. The Big Bang Theory doesn't merely describe a distant event. It reveals that we are all interconnected, part of a vast and beautiful universe that began in an unfathomable moment of creation. And as we continue to unravel the mysteries of that moment, we are reminded that the quest for knowledge is, in itself, a journey that defines what it means to be human. The exploration of the universe's origin naturally leads us to consider its ultimate fate. Just as the Big Bang Theory suggests a beginning, the question of an end looms over the field of cosmology, inspiring theories about how the cosmos might one day cease to exist or transform into an entirely new state. Scientists have formulated several hypotheses about the universe's end, each one as fascinating as it is mysterious. Among the most discussed are the Big Crunch, the Big Freeze, and the Big Rip. Each theory paints a unique picture of the future, and all hinge on the forces currently shaping the universe: gravity, dark energy, and the enigmatic dark matter. In the Big Crunch scenario, gravity takes center stage. This hypothesis proposes that the gravitational pull between all objects could eventually slow the expansion of the universe, reversing it into a collapse. Galaxies, stars, and all cosmic structures would draw closer together, merging into one superheated mass. As space itself contracts, the universe would become denser and hotter, eventually converging back to a singularity, much like the one believed to have sparked the Big Bang. It would be an end where everything converges back into an infinitely dense point, perhaps setting the stage for another bang in a cycle of expansion and collapse. Contrastingly, the Big Freeze presents a scenario in which dark energy dominates, continuing to drive the expansion of the universe indefinitely. Dark energy, thought to make up about 68% of the universe, works in opposition to gravity by pushing galaxies apart at an accelerating rate. In this scenario, stars would burn through their fuel, leaving a universe of dark, cold remnants. Over trillions of years, galaxies would drift away from each other, and stars would exhaust their nuclear fuel, dimming one by one. Eventually, even black holes would dissipate due to Hawking radiation, leading to a universe that is cold, empty, and lifeless, a true cosmic freeze-out where no significant energy exchanges occur. The Big Rip theory takes the idea of dark energy to an even more dramatic conclusion. If the force of dark energy were to increase over time, it could eventually become strong enough to tear apart galaxies, stars, planets, and ultimately, even atomic structures. This escalation would mean that not only would galaxies drift apart, but even the particles within atoms would be ripped from each other, leading to a universe in which no structures, not even subatomic particles, could survive. It's a violent and final disintegration of all matter, a dissolution of reality itself. As we peer into these potential futures, we must also consider the mystery of dark matter. Although we can't observe dark matter directly, we infer its existence through its gravitational influence on galaxies and other cosmic structures. Dark matter plays a crucial role in holding galaxies together, acting as a kind of cosmic glue. Its exact nature remains elusive, but understanding dark matter could profoundly alter our predictions for the universe's fate. If dark matter exerts a stronger influence than we currently understand, it might counteract dark energy's influence in unexpected ways, possibly preventing a big rip or even contributing to a new theory about the universe's end. Further deepening these questions are theories about the multiverse, suggesting that our universe might be just one among countless others, each with different physical laws and fates. In some models, universes could be continuously created through quantum fluctuations, forming baby universes that could branch off from existing ones. This eternal inflation theory posits that universes are born and die in an unending cycle, an endless chain reaction of cosmos within a multiverse framework. If our universe were to reach a terminal end, other universes would continue to form, expanding the very concept of existence beyond a singular beginning or end. In the midst of these cosmic possibilities, quantum mechanics adds another layer of complexity. On the smallest scales, quantum mechanics governs particles in ways that defy traditional logic, allowing phenomena like superposition and entanglement. Some theories suggest that quantum fluctuations could prevent a total collapse, even in a big crunch scenario. Perhaps our universe could exist in a quantum state of superposition, both ending and beginning anew, with events unfolding differently based on subtle variations at the quantum level. This tantalizing idea implies that reality itself could be far stranger than our current understanding, with endings that are not truly ends and beginnings that emerge from nothing. As scientists continue their research, telescopes like the James Webb Space Telescope and projects observing the cosmic microwave background provide critical data, revealing more about the rate of expansion and the properties of dark energy. These tools help refine our understanding of the universe's structure and age, testing the limits of the Big Bang theory and expanding the realm of possible explanations for the cosmos's past and future. Considering the possibility of an eventual end or transformation invites us to reflect on our place in the cosmos. Humanity exists within a fleeting window of cosmic time, in an era where stars shine brightly and galaxies are visible. The light we observe from distant galaxies is a message from the universe's past, a view that will one day fade as expansion carries these galaxies beyond our observational reach. Our era is unique, a brief period where we can study the universe's history and anticipate its future. As we contemplate these scenarios, we are drawn back to the profound mystery of why the universe exists at all. Was there a purpose to the Big Bang? Or was it an event arising from random quantum fluctuations? The question remains open, as each answer brings new mysteries and insights. The universe, in its vast complexity, reflects a grand tapestry of forces and phenomena, both visible and invisible, that shape its journey. Through our study of the cosmos, we participate in this journey, piecing together the story of existence one discovery at a time. As long as we look to the stars and question our place among them, the quest for understanding continues. Whether the universe ends in fire, ice, or a final dissolution, each theory enriches our understanding and sense of wonder. And perhaps, in the search for answers, we might uncover truths about ourselves as well. The question of whether we are alone in the universe has captivated humanity for centuries. The search for extraterrestrial life goes beyond a mere fascination with aliens. It represents a profound quest to understand life's potential across the cosmos. Modern science has refined this search, guiding us from myth and speculation into rigorous exploration. We now know that conditions suitable for life might not be as rare as once thought, opening a door to countless possibilities about alien civilizations, microbial life, and even new biological paradigms that challenge our definitions of life itself. The discovery of exoplanets, planets orbiting stars outside our solar system, has been revolutionary. Since the 1990s, astronomers have confirmed thousands of these planets, many of which reside in the so-called habitable zone around their stars, where conditions could support liquid water. While the habitable zone alone doesn't guarantee life, it's a crucial factor. Observatories like the Kepler Space Telescope and, more recently, the Transiting Exoplanet Survey satellite TESS have broadened our catalog of exoplanets, revealing an astonishing diversity of planetary systems. Some of these planets, called super-Earths, are rocky worlds larger than our planet, potentially offering stable environments for life to thrive. But the presence of liquid water is just one ingredient for life. Scientists now look for biosignatures, chemical markers that could indicate biological activity. For instance, certain gases like oxygen, methane, and even phosphine, if found in the right concentrations and contexts, might hint at the presence of life forms. These gases can be produced by geological processes, but when found in combination, they might suggest biological processes. The search for these markers has advanced significantly with technologies capable of analyzing the atmospheres of distant planets. Upcoming telescopes, like the James Webb Space Telescope, are poised to study exoplanet atmospheres in unprecedented detail, pushing the search for biosignatures further than ever before. Yet, life could take forms far different from what we imagine. Astrobiology, the study of life's potential in the universe, has broadened its view of possible life forms beyond Earth-like conditions. We have discovered organisms on Earth, extremophiles, that thrive in environments once thought inhospitable, from boiling hot springs to acidic lakes and even deep under Antarctic ice. Such discoveries challenge our assumptions about the requirements for life, suggesting that alien organisms might thrive in extreme environments across the cosmos. This idea has led scientists to consider moons like Europa and Enceladus, where subsurface oceans beneath icy crusts could harbor microbial life. These moons orbit gas giants like Jupiter and Saturn, where conditions are hostile on the surface but may be suitable for life in their hidden oceans. The search for intelligent extraterrestrial civilizations adds another layer of intrigue. Programs like SETI, Search for Extraterrestrial Intelligence, have scanned the skies for radio signals that might indicate intelligent life beyond Earth. The idea is that if other civilizations have developed technology, they might also be transmitting signals, either intentionally or as a byproduct of their technology. While we haven't detected a clear signal yet, the vastness of the universe means we've barely scratched the surface. Our technology might also limit us. Civilizations more advanced than ours could use communication methods beyond our comprehension, making the search even more complex. In addition to listening, we've sent messages into space in the hopes of making contact. The Arecibo message, broadcast in 1974 from Puerto Rico's Arecibo Observatory, was an attempt to reach any potential extraterrestrial civilizations with a coded message about humanity and our solar system. Additionally, the Voyager probes, launched in the 1970s, each carry a golden record with sounds, images, and messages from Earth, serving as time capsules for any civilization that might encounter them. These efforts underscore humanity's hope to connect with others, though the vast distances and timescales involved mean that any response could take millennia, if it arrives at all. The possibility of extraterrestrial life also forces us to confront the Fermi paradox. Named after physicist Enrico Fermi, the paradox arises from the contradiction between the high probability of alien civilizations existing and the lack of evidence for them. If the universe is so vast and old, why haven't we detected other civilizations? Some scientists propose that intelligent life might be exceedingly rare, or that civilizations might tend to self-destruct before they reach a stage where they can communicate with others. Alternatively, advanced civilizations could be deliberately avoiding contact, adopting a cosmic quarantine to observe less advanced species like ours without interference. Other explanations suggest that intelligent life might exist in forms we cannot yet perceive. Civilizations could be post-biological, having transcended their physical forms and existing in ways our science can't yet grasp. Some even propose that advanced civilizations might create simulations, entire artificial universes for research or recreation. If so, our universe itself could be such a simulation, with the beings we seek lying outside its confines. While speculative, these ideas highlight the vastness of possibilities when considering intelligence and technology beyond our experience. Mars, the red planet, is another focus in the search for life. Mars once had liquid water on its surface, and ancient riverbeds and lake basins suggest a planet that was once warmer and wetter. NASA's Perseverance rover, currently exploring Mars, is equipped to search for signs of past microbial life. By analyzing Martian rocks and soil, scientists hope to uncover microfossils or chemical signatures of ancient organisms. Mars represents a unique opportunity to study a nearby world that might have once harbored life, and a discovery of even simple microbial life would have profound implications for understanding life's potential across the cosmos. Some scientists believe life might travel through space via panspermia, a theory suggesting that life could spread between planets and even star systems. If microbial life could survive in space, as some experiments suggest, it might hitch rides on comets, asteroids, or debris ejected from impacts, potentially seeding other planets with life. Panspermia implies that life on Earth might not have originated here. Instead, it could be part of a larger cosmic ecosystem where life travels and evolves in multiple locations, a thought-provoking idea that expands our perspective on life's resilience and adaptability. Humanity's curiosity about extraterrestrial life is not only scientific, it also holds profound philosophical implications. Discovering life, especially intelligent life, would challenge our views on uniqueness and place in the cosmos. How would our societies, religions, and worldviews adapt to the knowledge that we are not alone? The realization could transform our understanding of existence, reshaping how we view ourselves in relation to the universe. The search for life beyond Earth is a testament to humanity's drive to explore and understand. As we develop new tools and refine our theories, we may one day find answers to questions that have captivated generations. Whether we discover microbial organisms beneath Europa's icy crust or detect a distant radio signal from a civilization light years away, each step forward brings us closer to understanding our place in the grand tapestry of the cosmos. The journey itself is as compelling as any discovery, a reminder that the universe is vast, mysterious, and full of potential waiting to be uncovered. The study of black holes has redefined our understanding of physics and the structure of the universe, revealing some of the most mind-bending phenomena known to science. Black holes are regions in space where gravity is so intense that nothing, not even light, can escape their pull. First theorized by Einstein's general relativity, black holes embody the extremes of physics, challenging the very fabric of space and time. Far from being rare anomalies, they are now understood to be abundant, playing essential roles in shaping galaxies and perhaps even influencing the evolution of the cosmos. At the heart of most galaxies, including our Milky Way, lies a supermassive black hole. These black holes contain masses equivalent to millions or even billions of suns, compressed into a region no larger than our solar system. The presence of a supermassive black hole exerts a gravitational influence that helps hold galaxies together, guiding the orbits of stars and regulating the formation of new stars. The exact process of how these giants form remains mysterious. Some theories suggest that they began as smaller black holes that consumed massive amounts of matter, growing over billions of years. Alternatively, they might have formed directly from large gas clouds in the early universe, bypassing the stages of smaller stars altogether. The area around a black hole is called the event horizon, the point beyond which nothing can return. When matter gets close to this boundary, it accelerates to extreme speeds, generating immense energy and emitting high-energy radiation. As gas and dust spiral into the black hole, they form an accretion disk that can reach temperatures of millions of degrees. This process emits X-rays and other energetic forms of light, which astronomers can observe, revealing the presence of black holes even though the objects themselves are invisible. The radiation emitted by these accretion disks is among the most energetic phenomena in the universe, often outshining the entire host galaxy. One of the most fascinating aspects of black holes is their connection to space-time. According to Einstein's theory of general relativity, massive objects warp the fabric of space and time, and black holes represent this effect to the extreme. The intense gravitational pull of a black hole stretches space-time around it, creating what we perceive as gravity. Near a black hole, time itself slows dramatically, an effect known as gravitational time dilation. If an observer were to approach a black hole, they would experience time differently from someone farther away, effectively slowing down relative to the rest of the universe. This leads to the concept of singularity, a point within the black hole where density becomes infinite and the laws of physics as we know them break down. At the singularity, our current understanding of gravity and quantum mechanics collides, creating a puzzle that physicists have been trying to solve for decades. The search for a theory of quantum gravity, one that can unify quantum mechanics and general relativity, aims to explain the nature of singularities. Understanding what happens at a black hole's core could reveal deeper insights into the fundamental structure of the universe. Hawking radiation adds another layer of intrigue to black holes. In the 1970s, physicist Stephen Hawking theorized that black holes are not entirely black, but emit radiation due to quantum effects near the event horizon. This radiation implies that black holes slowly lose mass over time, eventually evaporating. If correct, this concept suggests that black holes are not eternal. Instead, they gradually diminish until they disappear, leaving behind no trace of the matter they consumed. This revelation sparked a profound debate in physics about the information paradox. If information about particles that fall into a black hole is lost when it evaporates, it contradicts the laws of quantum mechanics, which state that information cannot be destroyed. Resolving this paradox is one of the most significant challenges in modern physics. Black holes come in different sizes and varieties, from the supermassive giants at galactic centers to stellar mass black holes formed by the collapse of massive stars. When a star more than about 20 times the mass of the Sun exhausts its nuclear fuel, it can no longer support itself against gravitational collapse. The core collapses under its own weight, creating a stellar mass black hole. These black holes often exist in binary systems with a companion star, where they siphon matter from their partner, creating powerful X-ray emissions that astronomers detect. Observing these stellar mass black holes helps scientists understand both the life cycle of stars and the broader processes that shape galaxies. Recently, the discovery of intermediate mass black holes has filled a crucial gap in our understanding. These black holes, with masses ranging from hundreds to thousands of solar masses, were once elusive, but recent observations have provided evidence of their existence. Intermediate black holes might form through the merger of smaller black holes or as remnants of massive stars, although their formation process remains uncertain. Their discovery hints at a complex spectrum of black holes, offering insights into the growth of supermassive black holes and the evolution of cosmic structures. Black holes may also play a role in the formation of gravitational waves. When two black holes orbit each other and eventually merge, they release massive amounts of energy in the form of gravitational waves, ripples in space-time that travel across the universe. These waves were first detected in 2015 by the Laser Interferometer Gravitational Wave Observatory, LIGO, confirming a prediction made by Einstein a century earlier. The detection of gravitational waves has opened a new window into the universe, allowing us to observe cosmic events that were previously invisible. Studying these waves provides a unique glimpse into the most energetic events in the universe, including black hole mergers and possibly even the collision of neutron stars. There is a growing curiosity about the possibility that black holes could serve as gateways to other regions of the universe, or even to other universes entirely. While speculative, some theories suggest that the immense gravitational fields of black holes could warp space-time to such a degree that they create tunnels or wormholes, connecting distant points in space and time. These ideas, while not yet proven, are rooted in the mathematics of general relativity and have inspired countless discussions about the potential for interstellar travel. If black holes could indeed act as shortcuts through the universe, they might offer a means to bypass the vast distances between stars and galaxies. The Event Horizon Telescope, EHT, made headlines in 2019 when it captured the first-ever image of a black hole shadow. This achievement provided direct visual evidence of a black hole's event horizon, allowing scientists to study its structure and surrounding environment. The image showed a bright ring around a dark center, the silhouette of the black hole's event horizon against the glowing accretion disk. Observations like this one allow astrophysicists to test theories of general relativity under the most extreme conditions. Future improvements in observational technology promise even more detailed images, offering new insights into the behavior of matter and energy in one of the universe's most extreme environments. Exploring black holes pushes the limits of our understanding, challenging us to rethink the very nature of reality. They represent both the endpoints of stellar evolution and the frontiers of scientific knowledge. Each discovery about black holes reveals new layers of complexity, shedding light on fundamental questions about gravity, space-time, and the nature of the cosmos. As scientists continue to study these enigmatic objects, black holes promise to remain a rich source of insights, transforming our understanding of the universe and the principles that govern it. In every observation of black holes, we glimpse not just the outer boundaries of physics, but also the depths of human curiosity and ingenuity. Our fascination with black holes is a reflection of our desire to understand the universe's most profound mysteries. With each discovery, we come closer to unlocking the secrets hidden within these cosmic giants, knowing that the journey itself is as significant as the answers we seek. The concept of time travel has long been a staple of science fiction, but it also holds a serious place in theoretical physics. As one of the most intriguing aspects of the universe, time travel challenges our understanding of causality, the fabric of reality, and the very nature of time itself. Physicists explore time travel through the lens of Einstein's theory of relativity, which suggests that under certain extreme conditions, time might not be as linear as it appears. If time travel is possible, it would have profound implications, altering our understanding of the past, present, and future, and forcing us to reconsider what we believe about reality. Einstein's theory of special relativity introduced the idea that time is not absolute but relative, depending on speed. As an object approaches the speed of light, time for that object slows down relative to a stationary observer, a phenomenon known as time dilation. This effect has been experimentally verified with atomic clocks placed on fast-moving planes, where the clocks aboard the planes tick more slowly than identical clocks on the ground. While this kind of time dilation does not enable travel to the past or future in the conventional sense, it suggests that time can be experienced differently depending on one's speed. At near-light speeds, a space traveler could experience only a few years while centuries pass on Earth, effectively traveling to the future. General relativity further expands on this by showing how gravity can warp space-time. Massive objects like stars and black holes bend the space-time fabric, creating gravitational time dilation. Near a black hole, time slows down relative to regions with weaker gravitational fields. This phenomenon, famously depicted in the movie Interstellar, suggests that if one were to orbit close to a black hole without falling in, they could experience time differently from someone far from the gravitational influence, effectively moving into the future. However, while this type of time travel to the future is theoretically possible, it doesn't allow us to revisit the past. Yet, the possibility of closed time-like curves, CTCs, essentially loops in time, introduces the concept of traveling back to earlier points in time. General relativity allows for the existence of such curves under specific, extreme conditions, like those found near rotating black holes or hypothetical wormholes. A rotating black hole, or Kerr black hole, could theoretically create a twist in spacetime that might enable closed time-like curves. However, to achieve time travel through such a structure would require navigating enormous gravitational forces and overcoming technical challenges beyond our current capabilities. The idea of wormholes as pathways through time is another captivating possibility. In theory, a wormhole connects two distant points in spacetime, potentially acting as a shortcut for space travel or even enabling movement between different times. Some physicists propose that if one end of a wormhole were accelerated to near-light speed and then brought back to its starting point, the two ends would be out of sync in time due to time dilation. This configuration could, in theory, allow travel between the two time-separated openings of the wormhole. However, stabilizing a wormhole and preventing it from collapsing would require exotic matter with negative energy, a substance that, while theoretically possible, has not been observed in practice. Exotic matter would act against the forces trying to close the wormhole, keeping the tunnel open and potentially making time travel possible. The potential for time travel introduces the grandfather paradox, a scenario where a time traveler could theoretically prevent their own existence by altering past events, like preventing their grandparents from meeting. This paradox raises questions about causality and the consistency of history. If events can be changed, how does reality reconcile contradictions? One possible solution is the many worlds interpretation, which suggests that any change in the past could create a new, parallel timeline, allowing both the altered and original timelines to coexist without contradiction. Under this interpretation, a time traveler would not be altering their original past, but rather branching into an alternate reality where different events unfold. Other physicists explore the concept of Novikov's self-consistency principle, which posits that any actions taken by a time traveler in the past must be consistent with the timeline they originated from. This principle suggests that paradoxes are impossible because any actions that would cause a paradox simply cannot happen. If one attempted to alter a past event that would prevent their own time travel, some force or consequence would intervene to prevent the paradox from occurring, preserving the original sequence of events. This approach implies that the universe has a form of built-in consistency, where time travel might be possible, but paradoxical changes are inherently restricted. Quantum mechanics adds yet another layer of complexity to the concept of time travel. In the quantum realm, particles can exist in superpositions, where they occupy multiple states simultaneously. Some physicists speculate that quantum mechanics could allow for quantum time travel, where a particle might interfere with its past self without causing a paradox. Recent experiments involving quantum entanglement and quantum teleportation suggest that information might be able to travel backward in time on a very small scale. However, this remains highly speculative and does not imply that humans could move backward in time in a meaningful way. Theoretical models of chronology protection suggest that the universe might contain inherent mechanisms to prevent time travel on a large scale. Physicist Stephen Hawking proposed a chronology protection conjecture, which argues that the laws of physics may prevent closed time-like curves and thus protect the universe from the chaotic effects of time travel. According to this conjecture, attempts to create time travel might automatically trigger natural forces that prevent such events from occurring, effectively protecting the timeline from disruption. While this remains theoretical, it hints at the possibility that the universe has self-regulating principles to maintain the consistency of time. Despite these hurdles, time travel remains a tantalizing possibility that scientists continue to explore. Advanced theoretical research delves into the nuances of space-time, seeking to unify general relativity with quantum mechanics in a theory of quantum gravity. Such a unification could provide new insights into time and causality, potentially opening the door to novel forms of time manipulation that are currently beyond our grasp. While time travel remains speculative, each step forward in our understanding of the universe brings us closer to answering whether time is as fixed as it seems. Ultimately, time travel challenges not just physics but also philosophical questions about free will, destiny, and the nature of existence. If time can be manipulated or traveled through, what does this mean for our choices and actions? Would a future with time travel imply that our actions are predetermined, or would it offer new dimensions of freedom? Such questions add depth to the scientific inquiry, intertwining time travel with our fundamental understanding of reality. As we push the boundaries of science, time travel remains one of the most profound and captivating mysteries, a topic that fuels imagination and drives scientific inquiry. While practical time travel may be far beyond our current capabilities, the exploration of its potential continues to inspire both physicists and dreamers alike. Whether or not we ever achieve time travel, the pursuit itself enriches our understanding of the universe, suggesting that time, like space, might be far more flexible and strange than we can currently comprehend. The concept of dark matter and dark energy has revolutionized our understanding of the cosmos, revealing that the universe is far more mysterious and complex than once thought. While ordinary matter, the stuff that makes up stars, planets, and everything we see, constitutes only about 5% of the universe, the rest is composed of dark matter and dark energy, enigmatic substances that do not interact with light and remain invisible to our telescopes. Together, they shape the structure and fate of the universe, influencing everything from galaxy formation to cosmic expansion. Dark matter was first proposed to explain why galaxies behave as they do. When astronomers observe galaxies, they notice something strange. The stars at the edges of galaxies orbit at nearly the same speed as those closer to the center. According to the laws of gravity, objects further from the center should move more slowly, as happens in our solar system. However, galaxies were not following this pattern. The only explanation was that a large amount of unseen mass, dark matter, was exerting gravitational pull, holding the galaxies together. This mysterious substance does not emit, absorb, or reflect light, making it invisible, but its presence can be inferred by its gravitational effects. One of the leading theories about dark matter suggests that it could be composed of weakly interacting massive particles, WIMPs. WIMPs would interact with normal matter only through gravity and the weak nuclear force, making them nearly undetectable. Scientists have built sensitive detectors, often located deep underground to shield them from cosmic rays, in hopes of observing WIMPs directly. Although none have been detected so far, the search continues, with new experiments pushing the boundaries of our detection capabilities. Another candidate for dark matter particles is axions, hypothetical particles with extremely low mass. Unlike WIMPs, axions would have even weaker interactions with matter, making them incredibly difficult to detect. However, their properties could match the observed behavior of dark matter on cosmic scales. Some experiments are now focusing on detecting axions through their predicted interactions with magnetic fields, a method that could reveal this elusive component of the cosmos. Recent theories have even suggested that primordial black holes could account for dark matter. These are black holes that might have formed shortly after the Big Bang, existing as relics from the early universe. Unlike black holes formed by stellar collapse, primordial black holes could be much smaller and more numerous, potentially filling the universe and contributing to the gravitational effects attributed to dark matter. Observing them, however, is incredibly challenging due to their small size and weak interactions with ordinary matter. Dark matter also plays a crucial role in the large-scale structure of the universe. Simulations show that dark matter forms a kind of cosmic web, with vast filaments connecting galaxies and clusters across billions of light years. Ordinary matter is drawn into these dark matter structures, forming galaxies within its gravitational framework. Without dark matter, the universe as we know it wouldn't exist. Galaxies would likely not have formed, and the stars and planets that fill them would be spread too thinly across space. This cosmic scaffolding suggests that dark matter is an essential component in the architecture of the cosmos, binding galaxies into clusters and superclusters. Then there is dark energy, a force that appears to work in opposition to gravity. Discovered in the late 1990s, dark energy was proposed to explain why the expansion of the universe is accelerating. Previously, astronomers believed that the universe's expansion, set into motion by the Big Bang, would gradually slow down under the influence of gravity. Instead, observations of distant supernovae revealed that galaxies are moving away from each other at an increasing rate. This acceleration requires an unknown energy source, dark energy, which now appears to make up about 68% of the universe's total energy content. One way to visualize dark energy is to imagine it as a property of space itself. According to Einstein's cosmological constant, space possesses an intrinsic energy that remains constant even as the universe expands. As more space is created with expansion, more dark energy is produced, fueling further acceleration. This self-reinforcing cycle explains why the universe's expansion is not slowing down, but speeding up. However, this explanation is still theoretical, as dark energy remains one of the greatest mysteries in modern physics. Some theories suggest that dark energy could be the result of a new, unknown field in physics. Unlike a constant, this field would change over time and vary across space, affecting the rate of expansion differently in different parts of the universe. If such a field exists, it would imply that our understanding of the universe is incomplete and that new physics awaits discovery. These ideas hint at possible links between dark energy and the forces of quantum mechanics, suggesting that dark energy might interact in ways we don't yet understand. The nature of dark matter and dark energy is so puzzling that it has led some scientists to consider modifications to general relativity itself. Alternative theories of gravity, such as MOND, modified Newtonian dynamics, and tensor vector scalar, TeVis gravity, propose adjustments to gravity's behavior on large cosmic scales, potentially eliminating the need for dark matter. These theories remain controversial, as they struggle to fully replicate the observed gravitational effects of dark matter. However, they are valuable in challenging our assumptions, showing that our understanding of gravity might not be complete. Dark matter and dark energy together make up 95% of the universe's total content, leaving ordinary matter as a minor component. This revelation profoundly shifts our perspective, suggesting that the visible universe is only a fraction of reality. The quest to understand these mysterious components pushes the boundaries of physics, inspiring new approaches and technologies in particle physics, cosmology, and astronomy. As telescopes like the James Webb Space Telescope and new gravitational wave observatories come online, our ability to explore the dark universe continues to expand. Upcoming observations of cosmic microwave background radiation, galaxy clustering, and gravitational lensing will provide more data on the distribution and behavior of dark matter and dark energy. Advanced experiments in particle physics aim to detect dark matter particles directly, while astronomers search for signs of dark energy's influence on cosmic structures. The mystery of dark matter and dark energy is a reminder of how much we have yet to learn about the universe. Each new discovery brings us closer to unraveling these secrets, but it also raises deeper questions. What are these invisible components that shape our reality? Could dark matter and dark energy be part of a larger framework of forces and particles beyond our current understanding? Perhaps they are hints of new dimensions, unknown particles, or fundamental forces waiting to be discovered. In our quest to understand the cosmos, dark matter and dark energy represent a frontier of science that challenges the limits of our knowledge. They compel us to rethink our place in the universe, revealing that what we can see and touch is only a small fraction of a much grander and more enigmatic reality. As scientists delve deeper into these mysteries, each breakthrough will bring us closer to comprehending the vast, hidden forces that govern the universe and, perhaps, unlocking new realms of existence. The possibility of extraterrestrial megastructures, massive constructions built by advanced alien civilizations, has captivated astronomers and scientists alike. These hypothetical structures, ranging from Dyson spheres to stellar engines, represent the pinnacle of technological achievement, created by civilizations vastly more advanced than our own. The search for these megastructures not only expands our understanding of what alien life might look like, but also pushes us to contemplate the future potential of humanity in the cosmos. The most well-known concept among extraterrestrial megastructures is the Dyson sphere. Proposed by physicist Freeman Dyson in 1960, a Dyson sphere is a structure built around a star to capture its energy output. A civilization capable of building such a structure, classified as a Type II civilization on the Kardashev scale, would harness the total energy produced by its star, granting it nearly limitless power. There are variations of the Dyson sphere concept, from a solid shell that completely encases a star to a Dyson swarm, a collection of solar-collecting satellites orbiting the star. The primary goal of such a structure would be to capture energy for advanced technological needs, potentially powering massive computational or industrial systems. Searching for Dyson spheres involves looking for infrared signatures. Since a Dyson sphere would absorb most visible light from its star but emit energy as heat, it would be detectable by observing an excess of infrared radiation compared to visible light. Projects like the Infrared Astronomical Satellite, IRAS, and the Wide-Field Infrared Survey Explorer, WISE, have scanned the sky, hoping to detect such infrared excesses, which could indicate the presence of a Dyson sphere. While no confirmed Dyson spheres have been found, the search continues, and each detection of unusual infrared signals adds intrigue to the question of whether we might one day find evidence of such a structure. Another concept is the stellar engine, a colossal construct designed to move an entire star system. This concept assumes a civilization so advanced that it could manipulate the gravitational balance of its home star to travel through the galaxy. The most popular design is the Shkadov thruster, a hypothetical stellar engine that uses a massive mirror to reflect light back onto the star, creating a small but continuous force. Over time, this could move the star and its surrounding planetary system, allowing a civilization to escape hazardous regions of space or simply explore the galaxy on an unimaginable scale. Detecting a stellar engine would be incredibly challenging, as it would appear as a subtle anomaly in the star's motion. A more speculative structure is the Matryoshka brain, an extension of the Dyson sphere concept designed for extreme computational power. A Matryoshka brain consists of multiple nested Dyson shells, each capturing the waste heat from the inner layers to power further computation. Such a megastructure could simulate entire universes or serve as a massive consciousness, perhaps embodying the mind of an advanced civilization. The energy requirements and precision necessary to build a Matryoshka brain are beyond our current technology, but such a construct offers a glimpse into what a post-human civilization could achieve, operating on a level that far exceeds our computational limits. Ring worlds and Niven rings are other fascinating possibilities. A ring world, originally envisioned by science fiction author Larry Niven, is a vast ring encircling a star at a habitable distance. Such a structure would provide an immense living area, potentially millions of times greater than Earth's surface. While physically constructing a ring world presents enormous challenges, including stability and material requirements, the idea of creating a habitat on such a scale reveals the possibilities that advanced engineering could unlock. Some theories even propose a more ambitious structure, the Alderson disk, which would create an artificial plane around a star, offering virtually unlimited space for a civilization. More recent scientific speculations have considered the potential existence of KIC 8462852, or Tabby's star, as an example of a potential megastructure. Observed to experience irregular and significant drops in brightness, the star's behavior defied explanations involving natural causes like planets or asteroids. Some propose that the star might be partially obscured by a Dyson swarm or another megastructure, causing the strange dimming pattern. Although further study revealed more likely explanations, such as interstellar dust, Tabby's star sparked renewed interest in searching for unusual astronomical phenomena that could indicate artificial structures. Beyond physical structures, the concept of computational megastructures or galactic-scale artificial intelligences, AI, has emerged in theoretical discussions. These intelligences, often called planetary brains or galactic minds, would use entire planets or even stars as computational resources, executing processes at speeds and scales unimaginable to human minds. Such entities could simulate vast realities, possibly even containing simulations of other universes or consciousnesses. In this speculative view, advanced civilizations might eventually transcend physical constructs entirely, becoming vast, disembodied intelligences distributed across the galaxy. Stellar lifeboats are another form of hypothetical megastructure. These structures would serve as a safeguard against cosmic catastrophes, designed to protect a civilization's population and knowledge. They might take the form of large space habitats or enclosed environments capable of enduring radiation, supernovae, or even galaxy-wide disasters. A civilization that anticipates risks on such a large scale might create self-sustaining habitats that could remain habitable indefinitely, independent of their home star system. The search for these megastructures relies on astronomical observations and anomalies. By analyzing patterns in starlight, gravitational waves, and energy emissions, scientists hope to detect irregularities that cannot be explained by natural processes. One approach involves analyzing transit data, where periodic dimming of stars suggests planets or objects passing in front. Anomalous transits, where dimming is uneven or irregular, could hint at structures like Dyson swarms or other megastructures. As observational technology improves, the search for extraterrestrial engineering continues to expand, driven by the notion that we might one day identify the unmistakable signature of advanced alien technology. The existence of extraterrestrial megastructures raises profound questions about the nature of intelligence and civilization. A society capable of building these constructs would have to overcome enormous technological, environmental, and social challenges. Such a civilization would likely be united in purpose, with long-term planning extending beyond thousands or even millions of years. This level of cooperation and foresight suggests that advanced societies might prioritize sustainability, energy efficiency, and cosmic exploration in ways that humanity has yet to achieve. Some scientists propose that the Kardashev scale might extend beyond Type 3 civilizations, those harnessing the energy of an entire galaxy, to hypothetical Type 4 or even Type 5 civilizations, capable of manipulating energy on a universal or multiversal level. These civilizations might not be bound by traditional physics as we know it, potentially having unlocked ways to manipulate space-time, energy, and matter at fundamental levels. This opens the door to speculation about technologies and capabilities that go far beyond our current scientific understanding, perhaps involving phenomena like black hole manipulation or even creating artificial universes. The search for megastructures also leads to ethical and existential questions. If we were to detect evidence of such an advanced civilization, what would it mean for humanity? Would we try to communicate, or would we choose to observe quietly, uncertain of how a vastly superior civilization might respond? The discovery of megastructures would redefine our place in the universe, revealing that civilizations can reach levels of technological prowess we can barely imagine. Such a discovery might inspire humanity to strive for greater achievements, or it might provoke fear of contact with beings far beyond our understanding. Ultimately, extraterrestrial megastructures represent the outer limits of what we envision possible. While speculative, they inspire us to think about the future of humanity and the potential trajectories of technological evolution. If these structures exist, they would not only signify intelligence but also a kind of cosmic scale, ambition, and perseverance, suggesting that civilizations capable of building megastructures endure for millennia, possibly eons. For now, we continue to search the stars, driven by the hope that one day we might find signs of such marvels, and in doing so, glimpse our own potential future among the stars. The concept of cosmic inflation has profoundly impacted our understanding of the universe's earliest moments, offering an explanation for the rapid expansion that set the stage for everything we observe today. Proposed in the 1980s by physicist Alan Guth, the theory of inflation suggests that, in the first fractions of a second after the Big Bang, the universe expanded at a rate far exceeding the speed of light, growing exponentially from a minuscule point to an incomprehensibly large size. This burst of expansion, lasting for only an instant, solved many of the puzzles that the traditional Big Bang theory alone couldn't address, and it has reshaped our view of how the cosmos came into being. One of the key questions cosmic inflation addresses is the horizon problem. When we observe the universe, we see that distant regions have nearly identical properties, such as temperature and density, even though they should have been too far apart to exchange any information or energy. According to standard cosmological models, there hasn't been enough time since the Big Bang for light or other signals to travel between these distant regions. However, inflation solves this by proposing that all parts of the universe were once close enough to equilibrate before inflation rapidly expanded them to vast distances. This process created the homogeneous universe we observe today, where distant regions have similar conditions. Inflation also provides a solution to the flatness problem. Observations show that the universe is almost perfectly flat, meaning that the geometry of space does not curve significantly on cosmic scales. However, without inflation, the universe should have either collapsed back on itself or expanded so quickly that it would appear extremely curved today. Inflation drives the universe toward flatness, much like how a balloon appears flatter as it inflates. By expanding space so rapidly, inflation ensured that even if the universe had some initial curvature, it would be negligible today, resulting in the flat geometry observed. Another profound implication of inflation is its ability to explain the formation of cosmic structure. During the inflationary period, quantum fluctuations in the fabric of spacetime itself were stretched to macroscopic scales, creating tiny density variations. As the universe continued to expand after inflation, these fluctuations became the seeds for galaxies, clusters, and all large-scale structures we observe. Essentially, inflation took microscopic quantum events and stretched them across the cosmos, leading to regions of varying density. Over billions of years, gravity amplified these fluctuations, allowing matter to coalesce into stars, galaxies, and cosmic structures. To probe inflation, scientists study the cosmic microwave background, CMB, the afterglow of the Big Bang. The CMB provides a snapshot of the universe approximately 380,000 years after inflation, when it cooled enough for photons to travel freely. Tiny temperature fluctuations in the CMB reveal the imprints of those early density fluctuations seeded by inflation. Observations from telescopes like the Wilkinson Microwave Anisotropy Probe, WMAP, and the Planck satellite have measured these fluctuations with incredible precision, supporting many predictions of inflationary theory. The uniformity and specific patterns in the CMB strongly suggest that inflation occurred, although the exact mechanisms remain the subject of ongoing research. Despite its success in explaining many features of the early universe, inflation raises questions that have yet to be fully answered. One of the biggest mysteries is what caused inflation to start and stop. Inflationary models often rely on a hypothetical field called the inflaton field, which drove the rapid expansion. However, scientists have yet to identify this field or the particle associated with it, and without direct evidence, inflation remains a powerful yet theoretical construct. Understanding the inflaton could potentially bridge gaps in our understanding of high-energy physics and bring us closer to a unified theory of the universe's fundamental forces. The theory of inflation also leads to the idea of a multiverse. In some inflationary models, the inflationary process never fully stops but continues in certain regions of spacetime, giving rise to bubble universes. Our observable universe would be just one bubble in this vast multiverse, with each bubble potentially having different physical properties and laws. This eternal inflation suggests an endless array of universes, each with unique characteristics, where everything that can happen does happen somewhere. While this multiverse concept is difficult to test directly, it remains a compelling solution to the origins of cosmic structure and diversity, expanding our understanding of what reality could entail. Furthermore, the theory of inflation intersects with quantum mechanics, leading to puzzling questions about the nature of reality. Quantum fluctuations during inflation, stretched across the cosmos, raise the idea that the universe itself may have arisen from a quantum event. In some models, the entire universe could have emerged from a quantum fluctuation in a pre-existing quantum field, a phenomenon sometimes called quantum creation. This idea suggests that the universe has no external cause. Instead, it is a spontaneous creation, arising from the fundamental principles of quantum mechanics. In recent years, scientists have sought evidence for primordial gravitational waves, another potential signature of inflation. During inflation, the rapid expansion of space would have generated ripples in spacetime, known as gravitational waves. These primordial waves would leave a distinct pattern in the CMB known as B-mode polarization, a subtle twisting pattern in the light. In 2014, scientists working with the BICEP 2 telescope announced the detection of these patterns, suggesting direct evidence of inflation. However, later analysis showed that dust in our galaxy could account for the observed patterns, meaning that primordial gravitational waves remain unconfirmed. The search for these gravitational waves continues, as their detection would provide compelling proof of inflation. One of the most exciting aspects of inflationary theory is its potential connection to a theory of everything, a unified framework that merges general relativity with quantum mechanics. Inflation takes place at energy scales where quantum effects of gravity would be significant, hinting that understanding inflation could provide insights into quantum gravity. Some theories, such as string theory and loop quantum gravity, attempt to reconcile gravity with quantum mechanics and suggest that inflation might be a natural consequence of these deeper principles. However, no theory has yet provided a complete picture, leaving inflation as a crucial clue in the search for a fundamental theory of nature. Inflation also brings us to the question of cosmic origins. If inflation created the universe we observe, what, if anything, preceded it? Some cosmologists propose that the Big Bang might not have been the absolute beginning, but rather a transition between different phases of the universe. Bounce cosmology, for example, suggests that the universe undergoes endless cycles of expansion and contraction. In this model, our current expansion phase began with a bounce rather than a singularity, potentially eliminating the need for an initial starting point. This idea provides an alternative view of inflation, incorporating it as part of a continuous, cyclic universe. The implications of inflation extend beyond science into philosophical realms. If inflation and the multiverse are correct, then our universe might be just one of countless others, each with different physical laws and constants. This perspective forces us to reconsider the nature of reality and our place within it. Are we simply one random occurrence among infinite possibilities? The multiverse view challenges the notion of a unique universe, suggesting instead a vast, cosmic landscape where every possibility is realized somewhere. As scientists continue to probe the cosmos, inflation remains one of the most compelling and mysterious theories in cosmology. It explains many aspects of the early universe, yet leaves us with profound questions about the nature of reality, the origins of space and time, and the potential existence of other universes. Each new observation, from CMB measurements to gravitational wave searches, brings us closer to understanding this cosmic burst and the events that set our universe on its current path. The story of inflation is in many ways the story of the universe itself. From a minuscule quantum fluctuation to a universe filled with galaxies, stars, and planets, inflation provides a glimpse into the extraordinary forces that shaped our reality. Whether we eventually confirm the details of inflation or find new theories to explain the early cosmos, the journey to understand our beginnings continues, revealing ever deeper layers of mystery and wonder in the fabric of the universe. The concept of quantum mechanics has transformed our understanding of the universe at its most fundamental level, revealing a reality that defies common intuition. Unlike the predictable world of classical physics, the quantum realm is governed by uncertainty, duality, and probabilities. Quantum mechanics not only explains the behavior of subatomic particles, but also challenges our understanding of reality, prompting questions about the nature of existence, measurement, and even consciousness. Since its inception in the early 20th century, quantum mechanics has given rise to technologies like lasers and transistors and has laid the groundwork for revolutionary ideas like quantum computing and quantum cryptography. At the core of quantum mechanics lies wave-particle duality, a principle stating that particles like electrons and photons exhibit both wave-like and particle-like properties. Experiments like the double-slit experiment demonstrate this duality vividly. When particles such as electrons pass through two slits, they form an interference pattern on a screen, suggesting wave behavior. However, if we observe which slit each particle passes through, the interference pattern disappears, and the particles behave as individual particles. This experiment shows that particles can exist in a superposition, embodying multiple states at once, until observed or measured. The phenomenon of superposition is one of the most mind-bending aspects of quantum mechanics. A particle in superposition can be in multiple states simultaneously, only collapsing into a single state upon measurement. This principle is famously illustrated by Schrödinger's cat, a thought experiment proposed by physicist Erwin Schrödinger. In this scenario, a cat inside a sealed box is simultaneously alive and dead, depending on the state of a radioactive atom. Until the box is opened and observed, the cat remains in a superposition of both states. Schrödinger's thought experiment highlights the strange implications of superposition, especially when applied to larger systems. Entanglement is another cornerstone of quantum mechanics, suggesting that particles can become correlated in ways that defy classical understanding. When two particles are entangled, the state of one particle is directly linked to the state of the other, regardless of the distance between them. This spooky action at a distance, as Einstein famously described it, implies that a change to one particle's state instantaneously affects its entangled partner, even if they are light years apart. Experiments have confirmed entanglement, showing that it is a fundamental feature of reality and challenging the notion of locality, the idea that objects are only directly influenced by their immediate surroundings. Entanglement is the basis for quantum teleportation, a process where the state of a particle is transmitted to another particle at a different location without moving the particle itself. While this doesn't mean physical teleportation as popularized in science fiction, it allows for the instantaneous transfer of information about quantum states. Quantum teleportation has been demonstrated over increasing distances, opening possibilities for quantum communication and quantum networks that could revolutionize data transfer with unprecedented speed and security. The Heisenberg uncertainty principle is a fundamental concept in quantum mechanics that places limits on what we can know about a particle's position and momentum simultaneously. The more precisely we measure one property, the less precisely we can know the other. This principle is not due to limitations in our measuring devices, but is intrinsic to nature itself. The uncertainty principle challenges the determinism of classical physics, where one could, theoretically, predict the future if all information were known. In the quantum realm, uncertainty is built into the very fabric of reality, suggesting that some aspects of the universe are fundamentally unknowable. Quantum mechanics also introduces the concept of probability in a way that contrasts sharply with classical physics. Instead of having definite positions and paths, particles are described by wave functions that provide a range of probable locations. When we measure a particle's position, the wave function collapses, yielding a single outcome from the set of probabilities. This probabilistic nature means that quantum mechanics does not provide certainty, but rather the likelihood of different outcomes. This randomness has profound implications for our understanding of causality and determinism. The many-worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett in the 1950s, provides one possible explanation for the uncertainty and superposition observed in quantum mechanics. According to this interpretation, all possible outcomes of a quantum event actually occur, but in separate, branching universes. Every time a quantum measurement is made, the universe splits into multiple versions, each containing a different outcome. In this multiverse framework, there is no collapse of the wave function. Instead, all possibilities are realized across an infinite number of parallel realities. While the many-worlds interpretation remains unproven, it offers a fascinating perspective on the nature of reality, where every possible history and future is realized somewhere. Quantum computing is one of the most promising applications of quantum mechanics. Traditional computers operate on bits, which are binary units that represent either a 0 or a 1. Quantum computers, however, use quantum bits or qubits, which can exist in superpositions of 0 and 1 simultaneously. This property enables quantum computers to process information in parallel, exponentially increasing their computing power for specific types of problems. Quantum computers hold potential for solving complex issues in cryptography, chemistry, and artificial intelligence, potentially transforming industries by solving problems that would take classical computers millions of years. In the field of quantum cryptography, quantum mechanics provides a level of security impossible to achieve with classical methods. Quantum key distribution, QKD, a method based on the principles of quantum mechanics, enables two parties to share a cryptographic key in a way that makes eavesdropping impossible. If a third party tries to intercept the key, the act of measurement will disturb the system, alerting the users to the presence of an intruder. This technology has been tested successfully and promises to revolutionize secure communication, ensuring privacy in a world where data security is increasingly paramount. Quantum mechanics also raises questions about the role of consciousness in measurement. Some interpretations suggest that the act of observation itself is what causes the wave function to collapse, determining the outcome of a quantum event. This idea, often associated with the Copenhagen interpretation, implies that consciousness plays a role in shaping reality, though this remains highly controversial and debated among physicists. The relationship between consciousness and quantum mechanics continues to be a topic of fascination and speculation, inspiring both scientific and philosophical inquiries into the nature of reality. Despite its successes, quantum mechanics is incomplete when it comes to describing gravity. The standard model of quantum mechanics works well for the three fundamental forces: electromagnetic, weak, and strong interactions. But gravity, described by general relativity, resists quantization. The pursuit of a theory of quantum gravity seeks to reconcile these two frameworks, leading to theories like string theory and loop quantum gravity, which aim to describe gravity in quantum terms. Solving this problem would provide a unified understanding of the universe at all scales, from the tiniest particles to the largest cosmic structures. As physicists continue to probe deeper into quantum mechanics, they find new mysteries that defy our classical intuition, pushing the boundaries of knowledge and technology. Quantum mechanics challenges our understanding of reality itself, suggesting a universe that is far stranger than anything we encounter in everyday life. Each discovery in quantum physics not only advances our technological capabilities, but also opens up new questions, inviting us to explore a realm where probability reigns. Particles exist in superposition, and entanglement connects objects across vast distances. The study of quantum mechanics forces us to confront the limitations of human perception and intuition. It reveals a reality where particles don't follow deterministic paths, where measurement influences outcomes, and where all possibilities might coexist in a vast multiverse. Quantum mechanics has reshaped physics, technology, and philosophy, leaving us with a profound sense of wonder and mystery about the very nature of existence. As we delve deeper into the quantum realm, we continue to uncover layers of complexity, each hinting that the universe is more intricate and interconnected than we could ever have imagined. The concept of black hole information paradox has sparked intense debate and exploration among physicists, as it challenges the fundamental principles of physics. Black holes, as regions of intense gravitational pull from which nothing, not even light, can escape, present a profound mystery when it comes to information preservation. In classical physics, information about a system state is never lost. However, black holes seem to defy this rule, leading to what is known as the information paradox. This paradox raises questions about the very fabric of reality, intertwining quantum mechanics, general relativity, and thermodynamics. The paradox emerged when Stephen Hawking demonstrated that black holes emit radiation due to quantum effects near their event horizons. This radiation, now called Hawking radiation, implies that black holes are not entirely black, but slowly evaporate over time, eventually disappearing completely. However, if a black hole evaporates and vanishes, what happens to the information about the particles that fell into it? In quantum mechanics, the principle of unitarity states that information about a system's initial state must be preserved over time. If black holes destroy information, it would mean that unitarity is violated, posing a fundamental conflict with the laws of quantum mechanics. Hawking radiation itself is a fascinating phenomenon that arises from quantum fluctuations near the event horizon. According to quantum mechanics, particle-antiparticle pairs are constantly created and annihilated in empty space. Near the event horizon, one of these particles might fall into the black hole while the other escapes as radiation. The energy for this process comes from the black hole itself, causing it to lose mass over time. This slow evaporation process means that a black hole with no new matter falling into it would eventually disappear, taking with it the information about everything it had absorbed. The information paradox has prompted various proposals to resolve this tension. One idea involves the concept of information being stored on the event horizon in the form of a hologram. This idea, known as the holographic principle, suggests that all the information contained within a black hole could be encoded on its two-dimensional surface area rather than within its volume. According to this view, the three-dimensional information we perceive is essentially projected from a two-dimensional surface. This principle has found broader applications in physics, suggesting that our universe itself might be a holographic projection from a lower-dimensional reality. The firewall hypothesis presents another approach to the information paradox. According to this hypothesis, instead of smoothly crossing the event horizon, any particle or observer approaching a black hole would encounter a firewall, an intense wall of high-energy radiation. This would prevent any information from truly entering the black hole, as it would be destroyed at the firewall. While controversial, the firewall hypothesis provides a potential mechanism for preserving information, though it contradicts the smooth transition predicted by general relativity and has yet to be widely accepted. A different line of thought is based on quantum entanglement and entanglement entropy. When particles become entangled, their states are correlated regardless of distance. As particles fall into a black hole, they remain entangled with their Hawking radiation counterparts. Some researchers propose that the information within a black hole is encoded in the entanglement between the particles that fell into the black hole and the particles radiated as Hawking radiation. This approach implies that the information isn't lost but rather scrambled in the radiation, possibly recoverable in theory if one had sufficient knowledge of the entanglement structure. The information paradox has also led to discussions about black hole complementarity, a principle that suggests different perspectives can coexist without contradiction. According to this principle, an observer outside the black hole sees information preserved on the event horizon, while an observer falling into the black hole experiences a different reality where they pass through the horizon without encountering a firewall. These two perspectives are mutually exclusive and consistent within their frames, creating a complementary description of black holes that maintains unitarity. In recent years, researchers have explored the concept of wormholes as a possible solution to the information paradox. In certain interpretations, black holes might be connected by wormholes or Einstein-Rosen bridges, creating shortcuts through space-time. Some theories suggest that these connections could provide a way for information to escape the black hole or remain accessible through quantum processes. While speculative, the connection between black holes and wormholes has fueled new lines of investigation, suggesting that black holes might serve as gateways rather than traps. Another fascinating approach is the soft hair theory, developed by Stephen Hawking, Malcolm Perry, and Andrew Strominger, which proposes that black holes possess soft hair, low-energy quantum excitations on their surface that store information. This theory suggests that rather than losing information, black holes store it in subtle, low-energy states on the event horizon. If correct, this approach would mean that black holes maintain a memory of the information they absorb, releasing it slowly through Hawking radiation, albeit in a highly scrambled form. The black hole information paradox has implications for a theory of quantum gravity, which aims to reconcile quantum mechanics with general relativity. Since black holes exist at the intersection of these two realms, understanding their behavior could provide insights into a unified theory. Some researchers have looked to string theory as a candidate for quantum gravity, as it describes particles and black holes as tiny vibrating strings. In string theory, black holes are seen as fuzzballs, collections of strings with no singularity or event horizon. The fuzzball concept suggests that information is stored within the strings, potentially solving the information paradox by eliminating traditional event horizons. The ADS/CFT correspondence has also provided insights into the paradox. This correspondence, proposed by physicist Juan Meldacena, suggests a relationship between a higher dimensional gravity theory, ADS, or anti-de Sitter space, and a lower dimensional quantum field theory, CFT, or conformal field theory, on its boundary. In this framework, a black hole in the higher dimensional space corresponds to quantum states in the lower dimensional theory, where information is preserved. The ADS/CFT correspondence offers a powerful tool for studying black holes, as it provides a dual description in which information is maintained, suggesting that information is not lost but transformed. These competing theories and interpretations illustrate the complexity and depth of the black hole information paradox. Despite decades of exploration, no single solution has been universally accepted, highlighting the challenge of reconciling quantum mechanics and general relativity. The paradox has become a touchstone in the quest for a deeper understanding of the universe, influencing fields as diverse as particle physics, cosmology, and information theory. The quest to solve the information paradox continues to inspire new lines of inquiry, pushing the boundaries of theoretical physics and deepening our understanding of the universe's most enigmatic objects. Black holes, once thought to be cosmic voids, now appear as dynamic entities rich with hidden information, quantum connections, and potentially transformative insights into the nature of reality. As we continue to probe the mysteries of black holes, we are reminded that the universe is stranger and more intricate than we could have imagined. Whether the information paradox leads to a solution through holography, entanglement, quantum gravity, or a yet undiscovered theory, each step forward in this journey brings us closer to unraveling one of the deepest mysteries of the cosmos. In the end, black holes may not only hold secrets about information, but could also provide the key to a unified understanding of physics itself. The exploration of wormholes, theoretical passages through space-time that could connect distant regions of the universe, has long captured the imagination of both scientists and the public. Often described as shortcuts or tunnels through space and time, wormholes challenge our understanding of physics, inviting us to consider the possibility of faster-than-light travel, intergalactic exploration, and even time travel. While wormholes have yet to be observed directly, they are a natural prediction of Einstein's theory of general relativity and remain a vibrant area of theoretical research, with potential implications for our understanding of space-time, black holes, and quantum gravity. The concept of wormholes can be traced back to Einstein and Nathan Rosen, who in 1935 proposed the existence of bridges in space-time that could connect two distant points. These bridges, now known as Einstein-Rosen bridges, were later popularized as wormholes. In their simplest form, a wormhole would consist of two ends, each at a different point in space-time, connected by a throat or tunnel. According to general relativity, such structures could theoretically exist if space-time is warped to an extreme degree, creating a shortcut through the fabric of reality. However, Wormholes would require incredibly precise conditions to remain stable and traversable. One of the challenges with wormholes is that they tend to be unstable. If a wormhole were to form, it would collapse almost instantly due to gravitational forces, closing the connection and making travel impossible. To keep a wormhole open, scientists propose the need for exotic matter, a type of matter with negative energy density that could counteract the gravitational pull, stabilizing the wormhole. Negative energy, while hypothetical, has been observed in small amounts in quantum phenomena, such as the Casimir effect, where two uncharged parallel plates create a tiny negative energy field between them. If exotic matter could be generated in sufficient quantities, it might theoretically stabilize a wormhole, allowing it to remain open for extended periods. The potential for time travel through wormholes is one of the most intriguing and controversial aspects of wormhole theory. If one end of a wormhole were accelerated to near the speed of light and then brought back to its original position, time dilation effects, predicted by special relativity, would cause that end of the wormhole to age more slowly than the other. This would create a time difference between the two ends, theoretically allowing someone to enter the wormhole at one end and emerge at the other end at an earlier or later time. This idea opens up possibilities for both future and past travel, although it raises profound questions about causality and the potential for paradoxes, such as the grandfather paradox. Wormholes also provide a potential solution to the black hole information paradox. If black holes and wormholes are interconnected, information that falls into a black hole might not be lost, but instead transferred through a wormhole to another part of the universe, or even to a parallel universe. In some theories, black holes could be gateways to other regions of space-time, with wormholes acting as exit points elsewhere. This idea has been explored in holographic duality and ADS/CFT correspondence, where black holes have a dual description in lower dimensional quantum theories, suggesting that wormholes could preserve information in ways we do not yet fully understand. Recent studies on quantum entanglement have suggested a possible relationship between entangled particles and wormholes. Some physicists propose that when two particles are entangled, they might be connected by a microscopic wormhole, allowing them to influence each other instantly, regardless of distance. This idea, known as ER equals EPR, Einstein-Rosen bridges equals Einstein-Podolsky-Rosen entanglement, proposes that entangled particles are linked by tiny wormholes. While this theory remains speculative, it offers a fascinating perspective on the connection between quantum mechanics and gravity, suggesting that wormholes might exist on a quantum scale as well as on cosmic scales. Wormholes, if they exist, could provide a means of interstellar travel far beyond the limits of conventional propulsion technology. In science fiction, wormholes are often depicted as gateways that allow for nearly instantaneous travel between distant points in space, bypassing the vast distances that would take millennia to cross at sublight speeds. Theoretically, a stable wormhole could allow humans to travel to distant galaxies in a matter of moments. However, the challenges of creating, stabilizing, and safely traversing such a structure are immense, involving physics far beyond our current capabilities. The possibility of using wormholes as communication channels across vast distances is another area of exploration. Since a wormhole could link 2 points in space directly, signals sent through it would bypass the intervening space, allowing for instantaneous communication across light years. This capability would revolutionize communication with distant space probes or colonies, eliminating the delays caused by the vastness of space. However, just as with physical travel, the stability and reliability of a wormhole as a communication link would depend on overcoming the challenges of exotic matter and wormhole maintenance. Some theories suggest that wormholes might naturally form in the early universe. During the Big Bang, intense gravitational forces and rapid expansion could have created tiny, short-lived wormholes as space-time fluctuated. While these primordial wormholes would likely be minuscule and unstable, they provide a basis for considering the natural formation of wormholes in highly energetic environments, such as the cores of stars or near black holes. Detecting such wormholes would be extremely challenging, as they would be nearly microscopic and may not last long enough to observe directly. The cosmic censorship conjecture is a principle that suggests singularities, points of infinite density, like those at the center of black holes, should not be visible from the outside, hidden by an event horizon. If wormholes could connect regions with different singularities, they might violate this principle, exposing singularities to distant observers. This raises questions about whether wormholes are compatible with general relativity or whether their existence would require a new understanding of gravity that allows for naked singularities, points in space where gravity becomes infinitely strong without an event horizon. In the context of quantum gravity, wormholes might provide insights into a unified theory of the universe's fundamental forces. The merging of quantum mechanics with general relativity remains one of the most significant challenges in theoretical physics, and wormholes sit at the intersection of these fields. Some approaches to quantum gravity, such as string theory and loop quantum gravity, suggest that space-time itself is a dynamic, interconnected fabric where wormholes could naturally arise. Understanding the physics of wormholes could bring us closer to a theory that unites gravity with the other fundamental forces. Although no direct evidence of wormholes has been found, scientists continue to explore ways to detect them. If a wormhole exists near a black hole, it could produce unusual gravitational lensing effects, bending light in ways that differ from a simple black hole. Observing such lensing effects with precise instruments could provide indirect evidence for the existence of wormholes. Gravitational wave detectors, which measure ripples in space-time, might also detect anomalies caused by wormhole interactions, although distinguishing such signals from other cosmic events would be challenging. Ultimately, the study of wormholes invites us to reconsider the nature of space-time, causality, and the boundaries of reality itself. Whether or not wormholes exist, exploring their theoretical properties has led to significant advancements in physics, from insights into black holes and quantum entanglement to ideas about the fundamental structure of space-time. Wormholes remain a tantalizing possibility, embodying humanity's desire to explore and understand the universe in ways that stretch our imagination and challenge our understanding. As we probe deeper into the mysteries of the cosmos, wormholes serve as symbols of both the known and the unknown. They represent the possibility of cosmic shortcuts, pathways to distant worlds, and perhaps even connections to other dimensions or parallel universes. While they remain speculative, the pursuit of wormholes continues to inspire scientists and dreamers alike, reminding us that the universe is full of possibilities that are as thrilling as they are enigmatic. In the quest to understand wormholes, we may ultimately find ourselves uncovering some of the deepest secrets of existence, transforming our understanding of space, time, and the universe's hidden dimensions. The study of parallel universes, alternate realities existing alongside our own, is one of the most mind-bending and speculative areas in modern physics. The concept challenges our understanding of existence and the boundaries of reality, suggesting that there may be an infinite number of universes, each with its own unique properties, histories, and outcomes. Often referred to as the multiverse, this theoretical landscape opens up possibilities that extend beyond the observable universe, inviting questions about whether other versions of ourselves, Earth, or even entirely different laws of physics might exist in these alternate realms. One of the most widely discussed frameworks for parallel universes comes from quantum mechanics and the many-worlds interpretation. Proposed by physicist Hugh Everett in the 1950s, the many-worlds interpretation suggests that every quantum event leads to a branching of the universe. When a particle exists in a superposition of states, each possible outcome corresponds to a new, separate universe. In this view, all possible histories and futures are realized in an infinitely branching tree of realities. For instance, in one universe, an electron might pass through one slit in a double-slit experiment, while in another, it passes through the other. The many-worlds interpretation allows for each possibility to exist without requiring wave function collapse, creating a vast multiverse where every choice and quantum event spawns a new reality. Another perspective on parallel universes arises from cosmic inflation, the rapid expansion of the universe in its earliest moments. Inflationary theory suggests that our universe is part of a larger bubble, with other bubble universes forming in different regions of space. These universes, created by ongoing cosmic inflation in different parts of the multiverse, might have vastly different properties, depending on the conditions present when each bubble formed. This idea, known as eternal inflation, implies an infinite landscape of universes, each potentially governed by unique physical constants, dimensions, and forms of matter. Our universe, in this view, is just one bubble in a vast cosmic foam of other bubbles. The brain multiverse model, inspired by string theory, proposes that our universe might be a three-dimensional brain floating within a higher dimensional space. According to string theory, reality consists of multiple dimensions beyond the familiar three of space and one of time, suggesting that other three-dimensional brains could exist parallel to ours. In this model, each brain could contain its own universe with distinct properties, and collisions between brains could even produce new universes in a process resembling the Big Bang. Some theories suggest that dark matter could be a manifestation of gravitational forces from a nearby brain, giving us a tantalizing hint of interactions with parallel universes. The quantum multiverse concept also arises in theories of quantum gravity, particularly in the quest to reconcile general relativity with quantum mechanics. Some physicists propose that the universe may have multiple branches on a quantum level, with each branch representing a different possible history. In certain quantum gravity frameworks, such as loop quantum cosmology, the Big Bang could have been a bounce from a previous collapsing universe, leading to the possibility that our universe has cyclically interacted with other universes across an infinite timeline. The holographic principle offers yet another perspective on the multiverse. This principle suggests that our three-dimensional reality might be a projection of information stored on a two-dimensional boundary, similar to a hologram. If true, this would imply that our universe is one of many possible configurations, existing as a kind of slice of a larger structure. In the context of AD/CFT correspondence, a theoretical framework in physics, our universe's physics could be mirrored by a lower-dimensional quantum theory on a boundary, potentially suggesting that other slices could represent parallel universes with alternate realities. Parallel universes are also considered in alternate histories and decision-based branching in hypothetical models of time travel. If traveling back in time changes events, each altered decision might spawn a new universe where a different outcome unfolds. In this view, if someone were to travel back and make even a small change, they could create a new reality that diverges from the original timeline, with both timelines existing as separate parallel worlds. This scenario, often explored in science fiction, touches on the grandfather paradox and illustrates the philosophical questions of free will and determinism that parallel universe theories invoke. Physicists have attempted to explore the existence of parallel universes through observable implications in our own universe. For example, collisions between bubble universes in the inflationary model could leave imprints in the cosmic microwave background, CMB, the afterglow of the Big Bang. Scientists search for unusual patterns in the CMB that might suggest our universe interacted with another bubble at some point in its early history. Although no definitive evidence has been found, studying these imprints remains a compelling avenue for indirect evidence of parallel universes. Another potential sign of a multiverse comes from fine-tuning in our universe's fundamental constants. Certain physical constants, like the strength of gravity or the cosmological constant, seem to be precisely balanced to allow the formation of galaxies, stars, and ultimately life. This fine-tuning has led some scientists to consider the anthropic principle, which suggests that if there are infinite universes, we naturally find ourselves in one of the few that has the right conditions for life. In this view, our universe's seemingly special conditions are not unique, but simply one of many variations in an infinite multiverse. Some scientists propose that dark matter and dark energy might hint at interactions with parallel universes. Dark matter, an invisible substance that makes up about 27% of the universe, has gravitational effects on galaxies but does not interact with ordinary matter or light. One speculative idea is that dark matter could be influenced by the gravity of a parallel universe, or that it represents a type of matter from a neighboring brane or bubble universe. Similarly, dark energy, responsible for the accelerated expansion of the universe, might reflect an unknown interaction with hidden dimensions or parallel realities. Despite the theoretical intrigue, experimental evidence for parallel universes remains elusive. Multiverse theories are challenging to test, as other universes would, by definition, exist outside our observable universe and may be governed by entirely different physical laws. However, as our understanding of physics progresses, scientists are developing new tools and models to explore these possibilities. For instance, advances in quantum computing, particle physics, and cosmology may one day reveal evidence of extra dimensions or provide indirect proof of multiverse interactions. The idea of parallel universes has profound philosophical and existential implications. If alternate versions of ourselves exist in other realities, it raises questions about identity, free will, and the nature of self. Are these other selves truly independent, or are they extensions of a single consciousness spread across different realities? The multiverse concept also challenges traditional notions of causality, as every possible event would occur in some universe, suggesting that reality is an endless branching tree where all possibilities are realized. The possibility of a multiverse has inspired both excitement and skepticism within the scientific community. Critics argue that because parallel universes are largely unobservable, the idea veers into metaphysics rather than science. However, proponents maintain that multiverse theories provide a valuable framework for understanding the fundamental nature of existence, offering explanations for phenomena like cosmic inflation, fine-tuning, and quantum behavior. For some, the multiverse represents a natural extension of the mathematical possibilities inherent in quantum mechanics and cosmology. Parallel universes push us to contemplate a reality far beyond our everyday experience, one where the boundaries of space, time, and existence itself are fluid and expansive. They offer a vision of the cosmos that is limitless, with infinite variations on reality playing out across vast realms of possibility. Whether or not we ultimately prove the existence of parallel universes, exploring these ideas enriches our understanding of what might be possible, challenging us to rethink our place in a potentially infinite multiverse. In pursuing the mysteries of parallel universes, we not only explore the outer reaches of science, but also confront the profound nature of existence. The multiverse, if real, would be a cosmic sea of realities, with each universe a unique expression of possibilities. As we delve deeper into these questions, we push the boundaries of human knowledge, seeking answers to some of the most profound questions about who we are and the ultimate structure of reality. The journey to understand parallel universes is as much a journey of self-discovery as it is a quest for scientific truth, offering glimpses into a cosmos that may be more intricate, interconnected, and wondrous than we ever imagined. The study of gravitational waves has opened a new frontier in astronomy and cosmology, allowing scientists to observe cosmic events that were previously undetectable. Predicted by Albert Einstein in 1915 as a consequence of his theory of general relativity, gravitational waves are ripples in the fabric of space-time, generated by the acceleration of massive objects like black holes or neutron stars. These waves propagate across the universe, carrying information about their cataclysmic origins and providing insights into the nature of gravity, space-time, and the structure of the universe itself. For decades, gravitational waves remained a theoretical concept because they are incredibly faint and challenging to detect. However, in 2015, nearly a century after Einstein's prediction, the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves. These waves were produced by the collision and merger of two black holes approximately 1.3 billion light-years away, marking the beginning of a new era in observational astronomy. This groundbreaking discovery confirmed Einstein's theory and opened up a new way to study the cosmos, effectively allowing us to listen to the universe. Gravitational waves are produced when massive objects undergo acceleration or violent interactions. The most common sources detectable on Earth are binary systems of compact objects, like black holes or neutron stars, orbiting each other and eventually merging. As these objects spiral closer, they accelerate, creating gravitational waves that radiate energy and cause the objects to draw even nearer. The final moments of this merger release a burst of gravitational waves, which can be detected as distinct chirps by observatories like LIGO and its European counterpart, Virgo. Each detection carries a unique signal, which encodes information about the masses, distances, and properties of the colliding objects. One of the most significant discoveries enabled by gravitational wave astronomy was the merger of neutron stars observed in 2017, known as GW170817. Unlike black hole mergers, which emit only gravitational waves, neutron star collisions also produce electromagnetic radiation, such as gamma rays, visible light, and X-rays. This multi-messenger event, detected in both gravitational waves and electromagnetic waves, allowed scientists to gain an unprecedented understanding of neutron stars and the origin of heavy elements. The collision produced a kilonova, a burst of energy believed to forge elements like gold, platinum, and uranium, providing insight into how these elements are scattered across the universe. Gravitational wave detection is accomplished through interferometers, such as LIGO, which use laser beams to measure incredibly small changes in distance caused by passing gravitational waves. Each LIGO observatory consists of 2 perpendicular arms, each 4 kilometers long, with laser beams traveling back and forth between mirrors at the ends of these arms. When a gravitational wave passes through, it slightly distorts space-time, changing the length of one arm relative to the other by a fraction of an atomic diameter. This tiny shift in distance is detected as an interference pattern, signaling the presence of a gravitational wave. The precision required for this detection is extraordinary, pushing the boundaries of current technology and engineering. Gravitational wave astronomy provides a unique window into phenomena that cannot be studied with traditional telescopes. Black hole collisions, for example, are invisible to electromagnetic observatories because they occur in regions where light cannot escape. Gravitational waves, however, penetrate these regions, allowing us to observe events in the otherwise hidden depths of the universe. This capability has transformed our understanding of black holes, neutron stars, and other exotic objects, providing insights into how these systems evolve and interact. The study of gravitational waves also holds promise for understanding cosmic inflation and the origins of the universe. Some theories suggest that inflation, the rapid expansion of the universe in its earliest moments, would have generated a background of primordial gravitational waves. Detecting these waves could provide direct evidence of inflation and reveal information about conditions in the early universe, just fractions of a second after the Big Bang. Such a discovery would offer a glimpse into the universe's most fundamental properties and the nature of space-time at its earliest stages. The detection of gravitational waves has also raised intriguing questions about dark matter and dark energy. Some scientists hypothesize that collisions involving hypothetical dark matter objects, such as primordial black holes or exotic particles, could produce unique gravitational wave signatures. By analyzing gravitational wave data, researchers might uncover indirect evidence of dark matter, offering new insights into this mysterious substance that makes up about 27% of the universe. Additionally, gravitational waves might interact with dark energy, the force driving the accelerated expansion of the universe, potentially providing clues about its nature. LISA, Laser Interferometer Space Antenna, a planned space-based gravitational wave observatory, represents the next step in gravitational wave detection. Scheduled for launch in the 2030s, LISA will consist of 3 satellites arranged in a triangular formation, with each side measuring millions of kilometers. By operating in space, LISA will be able to detect lower-frequency gravitational waves that are undetectable on Earth, enabling the study of massive black hole mergers, galactic binaries, and potentially even primordial gravitational waves from the early universe. LISA will extend our observational reach and allow us to explore gravitational phenomena on even larger cosmic scales. Gravitational wave astronomy also intersects with quantum mechanics, especially in the pursuit of understanding quantum gravity. Black hole mergers and neutron-star collisions occur in environments with extreme gravitational fields, where the effects of quantum mechanics and general relativity should interact in complex ways. Studying gravitational waves from these events could provide indirect evidence for a theory of quantum gravity, helping to bridge the gap between general relativity and quantum mechanics. Some researchers speculate that gravitational wave observations might reveal signatures of quantum effects, such as Hawking radiation or even microscopic black holes, which could offer clues to the fundamental structure of space-time. The advent of gravitational wave astronomy has also prompted researchers to think about the potential existence of gravitational wave backgrounds, persistent waves created by the superposition of countless weak signals from distant cosmic events. Similar to the cosmic microwave background, the gravitational wave background could provide a map of all past events involving massive objects, offering a new way to study the universe's history. Detecting this background would require highly sensitive instruments and collaboration between observatories around the world, representing a major challenge for future gravitational wave research. In addition to LIGO and Virgo, Kagra in Japan and Indigo in India are joining the global network of gravitational wave observatories. This growing network allows for more precise localization of gravitational wave sources, as multiple observatories can triangulate the origin of the signals. This improved accuracy in locating events enhances the chances of multi-messenger observations, where gravitational waves and electromagnetic signals from the same event are detected simultaneously. By expanding the global array of detectors, scientists are building a more comprehensive view of the universe, where each gravitational wave detection brings new insights into cosmic phenomena. The detection of gravitational waves has profound implications not only for physics, but also for philosophy and our understanding of reality. Gravitational waves provide direct evidence of the dynamic nature of space-time, reinforcing the concept that space and time are not fixed, but are shaped and molded by massive objects. This perspective challenges traditional notions of space and time as immutable backdrops, suggesting instead that they are fluid, interwoven with matter and energy in a cosmic dance. As we continue to detect and analyze gravitational waves, our understanding of the fundamental structure of reality evolves, revealing a universe that is far more interconnected and dynamic than we previously imagined. Gravitational wave astronomy is still in its infancy, but each detection marks a monumental leap in our knowledge of the universe. Every ripple in space-time tells a story of cataclysmic events, cosmic collisions, and the lives of stars and black holes. As technology advances and new observatories come online, we are likely to uncover even more phenomena that challenge our current understanding, reshaping our view of the cosmos in ways we cannot yet predict. In the end, gravitational waves are not just echoes of distant cosmic events. They are keys to a deeper understanding of the universe's history, structure, and fundamental laws. By listening to these faint signals, we unlock new realms of knowledge, opening doors to discoveries that promise to transform our view of existence and our place in the vast expanse of the cosmos. The study of gravitational waves represents a bold step forward in humanity's quest to understand the universe, a journey that promises to reveal wonders beyond our imagination and bring us closer to answering the most profound questions about the nature of reality. The concept of exoplanets, planets that orbit stars outside our solar system, has revolutionized our understanding of the universe and our place within it. The discovery of thousands of these alien worlds has expanded our vision of the cosmos, revealing a diversity of planets that challenge our assumptions about planetary formation, habitability, and even the potential for extraterrestrial life. With each new exoplanet discovery, we gain deeper insight into how planetary systems form and evolve, shedding light on the possibilities for life beyond Earth. The first confirmed detection of an exoplanet came in 1992, when astronomers identified two planets orbiting a pulsar, a rapidly spinning neutron star, 2,300 light-years away. These worlds, known as PSR B1257 plus 12b and PSR B1257 plus 12c, were a surprising discovery, as they defied expectations about where planets could form. Since then, the number of known exoplanets has grown exponentially, with groundbreaking missions like the Kepler Space Telescope and Transiting Exoplanet Survey satellite, TESS, leading the way in finding thousands of these distant worlds. Each detection adds a new chapter to our understanding of the universe, revealing planets orbiting various types of stars, some in stable orbits that could sustain life, others in extreme environments unlike anything seen in our solar system. One of the most significant aspects of exoplanetary science is the concept of the habitable zone, the region around a star where temperatures might allow liquid water to exist on a planet's surface. While liquid water is essential for life as we know it, finding planets in the habitable zone doesn't guarantee habitability. Atmospheric composition, planetary size, and magnetic fields all play a role in determining whether a world could support life. Nonetheless, the search for habitable zone exoplanets remains a major focus in the quest to find life beyond Earth. Kepler's observations, for example, have revealed many Earth-sized planets within the habitable zones of their stars, suggesting that potentially habitable worlds may be more common than previously thought. The diversity of exoplanets discovered so far is astonishing, challenging our understanding of planetary formation and evolution. Exoplanets come in a wide range of sizes, from super-Earths, planets larger than Earth but smaller than Neptune, to gas giants like Jupiter and Saturn, and even smaller rocky worlds similar in size to Mars and Mercury. Some exoplanets, known as hot Jupiters, orbit extremely close to their stars, resulting in temperatures that can exceed 1,000 degrees Celsius. These planets defy conventional models of planetary formation, as gas giants were initially believed to form only in the colder, outer regions of a solar system. The existence of hot Jupiters has led scientists to rethink their understanding of planetary migration, suggesting that giant planets can move inward after forming, influenced by gravitational interactions with their stars or other planets. Other exotic exoplanets, known as rogue planets, drift through space without orbiting any star. These planets likely formed within star systems, but were later ejected due to gravitational interactions. Rogue planets could outnumber stars in the galaxy, and some might retain heat through internal processes, potentially supporting subsurface oceans even in the frigid darkness of interstellar space. The discovery of rogue planets broadens our understanding of what constitutes a planet and suggests that planets are more abundant and varied than we previously believed. One of the most intriguing types of exoplanets is the water world, a planet with a significant portion of its mass composed of water. These worlds could have vast oceans covering their surfaces, creating environments very different from the continents and oceans of Earth. Water worlds, if they exist in habitable zones, might host alien marine life forms, possibly evolving in environments devoid of dry land. Observations of water-rich exoplanets remain indirect, but ongoing research into their atmospheres and densities could confirm the existence of such ocean-covered worlds. The search for exoplanets has also led to the discovery of super-Earths and mini-Neptunes, intermediate planets that don't exist in our solar system. Super-Earths are rocky planets larger than Earth, but smaller than Uranus and Neptune, and they may have thick atmospheres and high surface pressures. Mini-Neptunes are similar to Neptune, but are smaller and may have thick, hydrogen-rich atmospheres. These types of planets appear to be common in our galaxy, and their discovery has forced scientists to reconsider planetary classification and the conditions under which atmospheres and surfaces can exist. The techniques used to detect exoplanets are sophisticated and varied. The most successful method so far is the transit method, where astronomers observe the dimming of a star's light as a planet passes in front of it. By measuring the amount of dimming and the frequency of the transits, scientists can determine the planet's size and orbital period. Another method, the radial velocity method, measures tiny wobbles in a star's motion caused by the gravitational pull of an orbiting planet. These wobbles are detected through shifts in the star's spectrum and can provide information about the planet's mass. Once a planet is detected, astronomers often study its atmosphere to learn more about its potential habitability and chemical composition. Techniques like transmission spectroscopy analyze starlight as it passes through a planet's atmosphere during a transit, revealing absorption patterns that indicate the presence of gases like water vapor, methane, carbon dioxide, and possibly even biomarkers like oxygen or ozone. The detection of these gases could suggest a planet's suitability for life, as certain chemical signatures might indicate biological processes. For example, the recent detection of phosphine in the atmosphere of Venus sparked excitement because phosphine on Earth is associated with biological activity, although non-biological processes could also produce it. With the upcoming James Webb Space Telescope (JWST) and other advanced observatories, scientists expect to make even more detailed observations of exoplanet atmospheres. JWST's powerful instruments will allow astronomers to study the chemical compositions, temperatures, and atmospheric dynamics of exoplanets with unprecedented precision. JWST is expected to revolutionize our understanding of exoplanetary science, bringing us closer to detecting potential signs of life and exploring the atmospheric conditions of distant worlds. The discovery of exoplanets also raises questions about the Drake equation, a formula developed by Frank Drake in 1961 to estimate the number of extraterrestrial civilizations in the galaxy. With exoplanet data now available, scientists can refine some of the equation's parameters, such as the fraction of stars with planets and the number of planets that might support life. While the existence of habitable exoplanets does not guarantee intelligent life, it increases the chances that life might exist elsewhere in the universe. Each exoplanet discovery adds to our understanding of how common potentially habitable worlds might be, bringing us closer to answering the age-old question, are we alone? The study of exoplanets has also given rise to the field of astrobiology, which examines the conditions required for life and searches for biosignatures, chemical indicators that might suggest biological activity. While Earth-like conditions are often considered ideal for life, the diversity of exoplanets has led scientists to broaden their criteria, considering that life might exist in environments very different from those on Earth. Life on exoplanets could be based on alternative biochemistries, such as ammonia or methane instead of water, and silicon instead of carbon, challenging our assumptions about life's adaptability. The discovery of Earth-like exoplanets has profound implications for humanity. Knowing that potentially habitable worlds exist beyond our solar system invites us to consider our place in the universe, prompting philosophical questions about the uniqueness of Earth and the diversity of life in the cosmos. It also raises the possibility of future interstellar exploration and colonization. While the distances between stars make such journeys currently impractical, concepts like breakthrough propulsion and light sails are being explored as potential methods for reaching nearby exoplanets within a human lifetime. As we continue to study exoplanets, each new discovery reshapes our understanding of planetary systems and the potential for life elsewhere. The realization that our solar system is just one among countless planetary systems, each with its own unique structure and history, expands our vision of the cosmos and deepens the mystery of our own existence. In the search for exoplanets, we are not only exploring distant worlds, but also seeking to understand the conditions that led to life on Earth and the possibilities for life across the universe. Exoplanetary science is a dynamic and rapidly advancing field, with new discoveries and technologies constantly pushing the boundaries of our knowledge. Whether we find life on another planet or simply learn more about the diversity of planetary environments, the study of exoplanets is transforming our view of the universe. In the search for distant worlds, we find reflections of our own hopes, questions, and the enduring human drive to explore the unknown. The journey to uncover the secrets of exoplanets is one of the most exciting scientific quests of our time, a pursuit that promises to reveal new wonders and deepen our understanding of the cosmos and our place within it. The concept of cosmic strings offers a fascinating glimpse into the possible fundamental structure of the universe. Cosmic strings are hypothetical one-dimensional topological defects, incredibly thin but immensely dense, that may have formed during the early universe. These structures are thought to be remnants of the universe's birth, perhaps stretching across vast cosmic distances and potentially connecting different regions of space-time. If cosmic strings exist, they could provide insights into high-energy physics, the Big Bang, and even offer clues about unifying quantum mechanics and general relativity. Cosmic strings are theorized to have emerged during symmetry-breaking phase transitions that occurred when the universe was still in its infancy, shortly after the Big Bang. At high energies, it is believed that the four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were once unified. As the universe cooled, these forces began to separate in a series of phase transitions. These transitions might have created defects in the fabric of spacetime, much like cracks form in ice as it freezes. Cosmic strings are one-dimensional versions of these defects, potentially extending across millions of light years. One of the most remarkable features of cosmic strings is their extreme density and gravitational pull. Although they're only a billionth of a meter wide, cosmic strings could contain immense mass, with a single string potentially weighing as much as a large planet per kilometer. This density means that cosmic strings would produce intense gravitational fields, capable of bending light and warping spacetime around them. This gravitational influence could make cosmic strings detectable, as they would create distinctive patterns through gravitational lensing, where the path of light from distant stars or galaxies would be altered as it passes near a cosmic string. Gravitational lensing by cosmic strings would be unique and identifiable. Whereas normal gravitational lenses, such as those caused by galaxies or black holes, produce curved arcs or multiple images of the same object, a cosmic string would create double images separated by a sharp line. This distinctive lensing effect, often described as a cut in spacetime, would allow astronomers to differentiate between cosmic strings and other massive objects. Observing such lensing effects could provide the first direct evidence of cosmic strings and confirm aspects of early universe physics. Cosmic strings are also thought to produce gravitational waves. As these strings move and oscillate, they can create loops and kinks, which might eventually snap and release bursts of gravitational radiation. These events, known as cusps and kinks, would generate intense gravitational waves that could potentially be detected by observatories like LIGO or future gravitational wave detectors. Detecting these waves would provide a new way to study cosmic strings and understand the physics of the early universe, as the frequency and pattern of gravitational waves emitted by cosmic strings would be distinct from those produced by more familiar sources like black hole mergers. The existence of cosmic strings has significant implications for cosmology and our understanding of the universe's structure. If cosmic strings were created during the early universe, they might still persist today as relics, stretching across vast distances and linking distant regions of space. These strings could serve as cosmic highways, influencing the distribution of galaxies and contributing to the large-scale structure of the universe. Some theories suggest that cosmic strings might have played a role in seeding galaxy formation, providing gravitational scaffolding around which matter could coalesce during the universe's early stages. Cosmic strings also have a place in theories of cosmic inflation. Some models propose that inflation, the rapid expansion of the universe shortly after the Big Bang, could have stretched cosmic strings to enormous lengths, making them observable across large distances. The existence of cosmic strings could support certain inflationary models and offer clues about the energy scales at which inflation occurred. By studying cosmic strings, scientists could test and refine their models of inflation, gaining a deeper understanding of how the universe evolved from its initial state to its current configuration. In theoretical physics, cosmic strings are often explored within the framework of string theory and higher dimensional models. In some versions of string theory, fundamental particles are viewed as one-dimensional strings vibrating at specific frequencies, giving rise to the particle's properties. Cosmic strings, in this context, could be macroscopic manifestations of these fundamental strings, extended across spacetime in the form of massive one-dimensional defects. Additionally, in models that incorporate extra dimensions, such as those proposed by brain cosmology, cosmic strings could represent connections between different dimensions or even different universes. This idea suggests that cosmic strings might serve as bridges to parallel universes, adding a speculative but exciting dimension to their potential significance. The potential connection between cosmic strings and dark matter has also drawn interest. Some theories propose that cosmic strings could interact with dark matter, influencing its distribution across the universe. If cosmic strings exert gravitational influence over vast distances, they might help explain the large-scale structure of dark matter halos surrounding galaxies and galaxy clusters. Studying cosmic strings could thus provide insights into dark matter's properties, shedding light on one of the most elusive components of the cosmos. The quest to detect cosmic strings continues with the development of new observational techniques and instruments. Astronomers search for gravitational lensing patterns, gravitational wave signals, and cosmic microwave background (CMB) anomalies that might indicate the presence of cosmic strings. Observatories like the Square Kilometre Array (SKA) and future space-based gravitational wave detectors could play a critical role in this search, offering the sensitivity needed to detect the faint signals cosmic strings would produce. Cosmic strings are also tied to theoretical concepts like the multiverse. In some multiverse models, cosmic strings might exist at the boundaries between different universes or as remnants of interactions between bubble universes in an inflationary landscape. These strings could serve as conduits for information or energy transfer between universes, or even act as stitches in the cosmic fabric where different universes intersect. While highly speculative, the idea that cosmic strings could connect multiple universes adds an additional layer of intrigue to these theoretical structures, linking them to some of the most profound questions in cosmology. In addition to their role in fundamental physics, cosmic strings inspire philosophical and existential questions about the nature of reality and the structure of the universe. If cosmic strings are indeed relics of the universe's birth, they would be among the oldest structures in existence, predating galaxies, stars, and planets. They would serve as a direct link to the universe's origins, encapsulating the energy scales and physical laws that governed the earliest moments of time. Observing cosmic strings would be like peering back to the beginning of existence, offering a glimpse into a time before space, matter, and the forces we know had fully emerged. Despite their elusive nature, cosmic strings remain a topic of intense theoretical and observational research. While no direct evidence has been found, their existence is plausible within multiple frameworks of high-energy physics and cosmology. Whether they ultimately prove to be real or remain theoretical constructs, the study of cosmic strings pushes the boundaries of human knowledge, challenging us to consider a universe far more complex and interconnected than we ever imagined. In the pursuit of cosmic strings, we seek answers to some of the universe's deepest mysteries, from the nature of space-time to the origins of structure and the fabric of reality itself. Each new discovery or theoretical breakthrough brings us closer to understanding whether these one-dimensional relics truly exist and what role they play in the cosmic story. As science continues to advance, cosmic strings may become more than just theoretical curiosities, revealing themselves as fundamental threads woven into the tapestry of the cosmos, linking the universe's past, present, and perhaps even its future. The concept of panspermia suggests that life might not have originated on Earth, but could instead have been seeded here from elsewhere in the universe. This theory proposes that life, or at least the building blocks of life, may travel across space, spreading from one planetary system to another, either naturally or through intentional dissemination. The panspermia hypothesis challenges traditional views of life's origin, implying that life might be more resilient, widespread, and ancient than previously believed. It also raises intriguing questions about whether earthly life shares a common ancestry with life elsewhere in the cosmos. There are different forms of panspermia. Lithopanspermia is the idea that life can travel between planets or even star systems on meteoroids or comets. When large asteroids collide with planets, they can eject debris into space. If microorganisms are present in or on that debris, they could potentially survive the journey through space and reach another world. Studies have shown that certain extremophiles, organisms that can survive extreme conditions, might be capable of withstanding the cold, vacuum, and radiation of space for extended periods, increasing the feasibility of this process. The discovery of microbes that survive in harsh conditions, such as deep-sea vents and frozen Antarctic lakes, strengthens the case for lithopanspermia by demonstrating life's remarkable adaptability. Ballistic panspermia is a variant of this idea that suggests life might spread within a single planetary system. For instance, Mars and Earth have exchanged material through meteor impacts. Martian meteorites have been found on Earth, and some scientists speculate that Earth-originating material could have reached Mars as well. This exchange of material opens up the possibility that if life existed on one of these planets early in the solar system's history, it could have spread to the other. This hypothesis has led to speculation that life on Earth might have Martian origins, given that Mars likely had conditions suitable for life earlier than Earth did. The theory of radiopanspermia suggests that microscopic life forms could travel between stars, propelled by the pressure of starlight or cosmic radiation. Small particles, such as spores or tiny microbial cells, might be ejected from a planetary surface by volcanic eruptions or comet impacts. Once in space, they could be pushed by radiation pressure, potentially traveling vast distances. Although space is filled with harsh radiation that would be lethal to most known forms of life, certain extremophiles or spore-forming bacteria might be able to survive such a journey in a dormant state, reactivating only when they reach a suitable environment. Another fascinating variant is directed panspermia, the hypothesis that life on Earth or other planets was intentionally seeded by an advanced extraterrestrial civilization. Proposed by Nobel laureate Francis Crick, directed panspermia speculates that intelligent life elsewhere might have sent microbial life to Earth via spacecraft or specially designed probes, either to seed life or as part of a scientific experiment. While there is no evidence for this theory, it offers a framework for understanding how life might spread purposefully across the cosmos and raises philosophical questions about the potential for life forms to transcend planetary boundaries through technology. One of the strongest arguments for panspermia lies in the universality of life's building blocks. Organic molecules, including amino acids and nucleobases, the components of DNA and RNA, have been detected on meteorites, comets, and in interstellar clouds. The discovery of amino acids like glycine on comets, such as 67P/Churyumov-Gerasimenko, for instance, suggests that the basic ingredients for life may form easily in space and could be widespread across the galaxy. These molecules might have been delivered to young planets via comet and meteor impacts, seeding them with the necessary components for life to arise. The possibility of panspermia has driven interest in astrobiology and the search for life on other planets and moons within our solar system. Mars, for example, is a prime target due to its past potential for habitability. The discovery of microbial life on Mars, even if distinct from earthly life, could suggest that life can arise independently in similar environments. But if Martian life were genetically related to life on Earth, it would strongly support panspermia, indicating that life can transfer between planets. The icy moons Europa and Enceladus also intrigue scientists, as both are thought to harbor subsurface oceans beneath their icy crusts. Missions to these moons could test whether life might exist in environments outside Earth's habitable zone, potentially seeded by panspermia. In addition to studying life within our solar system, scientists are also examining interstellar objects for signs of panspermia. Objects like Oumuamua and 2I/Borisov are the first detected interstellar visitors passing through our solar system. While no evidence suggests they carried life, the discovery of interstellar objects opens up the possibility that debris from other planetary systems could carry organic compounds or even life across interstellar distances. Future missions to intercept and study these objects could reveal more about the conditions in other star systems and whether panspermia might occur on interstellar scales. Experiments have demonstrated that certain microbial life forms can survive the extreme conditions of space for extended periods. In the Tampopo experiment, for example, scientists placed spores of Deinococcus bacteria on the exterior of the International Space Station, ISS, to test their resilience. The spores survived for up to 3 years in the harsh vacuum of space, suggesting that microbial life could potentially endure long journeys between planets or star systems. Other experiments have shown that tardigrades, microscopic animals known for their extreme resilience, can also survive in space, supporting the idea that some forms of life could endure interplanetary or even interstellar travel. Panspermia has profound philosophical and existential implications. If life on Earth was seeded from elsewhere, it challenges the notion of Earth as a unique cradle of life and suggests that life might be more common throughout the universe. Panspermia also raises questions about the nature of life's origin, whether life arises spontaneously under the right conditions or whether it spreads from one location to another, driven by cosmic forces. If panspermia is true, it implies a form of interconnectedness among life forms across the universe, hinting at a cosmic lineage that transcends individual planets. Moreover, the possibility of directed panspermia raises questions about the potential motivations and ethics of a hypothetical advanced civilization seeding life. Would they have done so to cultivate life across the universe or as an experiment? Directed panspermia also inspires discussions about humanity's own future, as we explore other planets and potentially terraform or colonize them. The question of whether we might seed life elsewhere becomes increasingly relevant. Some scientists have even suggested that humanity could one day spread life intentionally, preserving Earth's legacy beyond our own solar system. Panspermia is difficult to prove, as the journey through space would likely destroy most biological signatures over time, erasing traces of its origin. However, ongoing research into extremophiles, resilient biomolecules, and interstellar objects may eventually provide evidence for or against panspermia. The discovery of life elsewhere in the solar system, particularly if it shares genetic similarities with earthly life, will be a strong indication that life is not confined to its planet of origin and that panspermia might play a role in spreading it across the cosmos. In the search for answers, missions like Mars Sample Return and the Europa Clipper may offer crucial insights into whether life can arise independently or whether it has a common origin shared across multiple worlds. If we discover that life on Mars or Europa is genetically related to life on Earth, it would strongly support the idea of panspermia within the solar system. On the other hand, if we find completely unrelated life forms, it would suggest that life can originate independently under the right conditions, expanding our understanding of life's adaptability and resilience. Panspermia continues to capture the imagination of scientists and laypeople alike, offering a vision of life as a cosmic phenomenon, not bound to a single world, but potentially dispersed throughout the galaxy. Whether we ultimately prove or disprove this theory, the study of panspermia encourages us to think about life in broader terms, as something not limited to Earth, but potentially present wherever the conditions allow it to take root. In contemplating panspermia, we explore our origins not just as earthbound beings, but as participants in a universe that may be teeming with life, linked by the invisible threads of cosmic evolution. The study of fast radio bursts, FRBs, has become one of the most intriguing fields in modern astrophysics. These mysterious, millisecond-long bursts of radio waves originate from distant galaxies, yet scientists still don't fully understand what causes them. Since their discovery in 2007, FRBs have captured the curiosity of astronomers around the world. They represent a cosmic enigma, prompting theories that range from highly magnetized neutron stars to the activity of alien civilizations. With the rapid advancement of radio telescope technology and data analysis, we are starting to unravel the nature of these extraordinary signals. Yet the full explanation remains elusive. Fast radio bursts are extraordinarily powerful, emitting more energy in a fraction of a second than our sun does in several days. Despite their intensity, they are challenging to observe because they occur so quickly and often don't repeat. Only some FRBs are known to repeat, which has allowed scientists to pinpoint their locations and gather more data. This distinction between repeating FRBs and non-repeating FRBs has led researchers to wonder if these bursts have multiple origins or mechanisms, with different astrophysical processes creating them. The discovery of FRBs happened somewhat by accident. In 2007, astronomers analyzing data from the Parkes Radio Telescope in Australia noticed a strange, single radio pulse that lasted only a few milliseconds. This was the first fast radio burst, now known as the Lorimer burst. Initially, some scientists thought it might have been a glitch or interference, but further observations confirmed that it was indeed a genuine cosmic phenomenon. Since then, hundreds of FRBs have been detected, and research has shifted from confirming their existence to understanding their origins. One of the leading theories suggests that FRBs are caused by highly magnetized neutron stars called magnetars. Magnetars are a type of neutron star with extremely strong magnetic fields, trillions of times stronger than Earth's. These magnetic fields are thought to be capable of generating powerful bursts of radio waves under specific conditions. In 2020, astronomers observed an FRB-like signal originating from a magnetar in our own Milky Way, providing the first direct evidence that magnetars could indeed produce FRBs. This discovery has strengthened the magnetar hypothesis, though it doesn't fully account for all FRBs, particularly those that repeat over long timescales. Another theory proposes that FRBs may result from the collisions of neutron stars or black holes. These cataclysmic events are known to produce powerful gravitational waves, and it's possible they could also generate short bursts of radio waves. However, this theory primarily applies to non-repeating FRBs, as these kinds of collisions would be one-time events. For repeating FRBs, another mechanism would need to be at play, suggesting that the diversity of FRB signals might stem from a variety of astrophysical sources. Some researchers have even suggested that FRBs might be signals from advanced alien civilizations. This idea is rooted in the fact that FRBs are highly energetic and can be detected across vast cosmic distances, making them suitable for long-range communication. Avi Loeb, a prominent astrophysicist, has speculated that FRBs could be powerful beams used by alien civilizations to propel light sails for interstellar travel. While there is no evidence supporting this, the sheer mystery surrounding FRBs leaves room for this hypothesis to be considered as a far-out possibility, reminding us of the need to keep an open mind as we explore unknown cosmic phenomena. In 2020, researchers used the Canadian Hydrogen Intensity Mapping Experiment (CHIME) to make significant strides in FRB detection. CHIME, a unique stationary radio telescope in British Columbia, Canada, scans the sky each day and has proven highly effective at capturing FRBs, detecting hundreds of bursts in just a few years. CHIME's contributions have expanded our FRB catalog, revealing new patterns and offering insight into the distribution of these bursts across the sky. For instance, some repeating FRBs exhibit periodic activity, with bursts occurring in regular intervals, which suggests that these sources might be orbiting other celestial bodies or have internal cycles of activity. The polarization of FRBs also provides clues about their origins. Polarization refers to the orientation of the electromagnetic waves in the burst, which can be affected by magnetic fields. By analyzing how FRB signals are polarized, scientists gain insight into the environment surrounding the source. Some FRBs show extremely high levels of polarization, hinting that they may originate near highly magnetized regions, such as those around magnetars or near black holes. The polarization data also allows researchers to study the magnetic fields they encounter on their journey to Earth, offering a unique method of probing the universe's structure. FRBs are not only intriguing due to their unknown origins, but also because they serve as cosmic probes. As these radio waves travel across the universe, they pass through various regions of space filled with ionized gas and plasma. The interaction between FRBs and this intergalactic medium causes a delay in different frequencies, known as dispersion. By studying the dispersion of FRB signals, scientists can learn about the density and composition of the intervening space. This characteristic makes FRBs useful tools for mapping the distribution of matter in the universe, including the elusive missing baryonic matter, ordinary matter that has been difficult to detect in space. Furthermore, the detection of FRBs has implications for cosmology and the study of dark energy. Since FRBs can be detected from billions of light years away, they offer a means to measure cosmic distances with high precision. This potential use of FRBs as standard candles, similar to Type Ia supernovae, could help astronomers refine measurements of the universe's expansion rate. Better understanding of the expansion rate would, in turn, provide new insights into dark energy the mysterious force driving the accelerated expansion of the universe. FRBs have also been linked to gamma-ray bursts, GRBs, another high-energy cosmic phenomenon. In some cases, FRBs have been observed in tandem with gamma-ray bursts, prompting scientists to explore whether they might share a common origin. Gamma-ray bursts are usually associated with massive stellar explosions or the formation of black holes, events capable of generating powerful electromagnetic emissions across multiple wavelengths. If certain FRBs are associated with GRBs, this connection could further constrain the possible origins of both phenomena and deepen our understanding of the most energetic events in the universe. As of now, the diversity among FRBs remains one of the most perplexing aspects of the phenomenon. Some FRBs are one-time events, while others repeat periodically or sporadically, suggesting that there may be multiple types of sources. Observations have shown that repeating FRBs often have different characteristics from one-time FRBs, such as variations in their spectra and polarization. This has led to the hypothesis that different classes of astrophysical objects, like magnetars, pulsars, or even exotic stars, could all produce FRBs under specific conditions, making FRBs a family of related phenomena rather than a single type of event. The study of FRBs is still in its infancy, and researchers are developing new methods to analyze the data and filter out false positives caused by human interference. Radio waves are highly susceptible to terrestrial interference, such as from cell phones, satellites, and even kitchen microwaves. To address this challenge, astronomers rely on complex algorithms to distinguish genuine cosmic signals from man-made noise, a process that has become more efficient as machine learning techniques have been applied to sift through massive data sets generated by telescopes like CHIME. In the coming years, next-generation observatories promise to expand our understanding of FRBs even further. The Square Kilometer Array (SK), an international radio telescope project set to become the largest and most sensitive radio telescope in the world, will play a critical role in FRB research. With its unprecedented sensitivity, SKA could detect fainter and more distant FRBs, potentially uncovering new types of bursts and further probing their origins. Additionally, SKA will allow for real-time detection and precise localization of FRB sources, enabling immediate follow-up observations across the electromagnetic spectrum. The mystery of fast radio bursts remains unsolved, yet each new observation brings us closer to understanding these enigmatic signals. They represent a new kind of cosmic puzzle, one that challenges our assumptions about the universe and the types of astrophysical processes that can occur. Whether they arise from neutron stars, black holes, alien technology, or something entirely unknown, FRBs have opened an exciting new window into the cosmos. In exploring FRBs, we not only aim to solve a scientific riddle, but also to expand our understanding of the universe's extreme environments and the potential forces at play across vast cosmic distances. The journey to understand fast radio bursts continues to captivate the astronomical community, promising discoveries that could reshape our understanding of the universe and reveal unexpected connections between seemingly unrelated phenomena. As we await the next breakthrough, FRBs remind us of the limitless potential for discovery in the ever-expanding universe. The exploration of antimatter is one of the most compelling fields in modern physics, as it challenges our understanding of the universe's structure, its origins, and the very nature of matter. Antimatter particles are counterparts to regular matter particles, identical in mass but with opposite charge. For every type of particle, there exists an antiparticle. For instance, the antiparticle of an electron negatively charged is a positron positively charged. When matter and antimatter meet, they annihilate each other in a burst of energy, a process that has profound implications for everything from particle physics to the early moments of the universe. The existence of antimatter was first predicted in 1928 by physicist Paul Dirac, who was attempting to reconcile quantum mechanics with special relativity. His equations revealed that for every particle, there should exist an opposite particle with the same mass but opposite charge. Shortly afterward, the positron, the antimatter counterpart to the electron, was discovered, providing the first confirmation of Dirac's theory. This discovery opened the door to the study of antimatter, revealing a parallel world of particles that mirrored the ordinary matter around us. One of the most intriguing questions about antimatter is the matter-antimatter asymmetry problem. According to the prevailing theories, the Big Bang should have created equal amounts of matter and antimatter. However, the observable universe is dominated by matter, with antimatter found only in trace amounts. If equal quantities of matter and antimatter were created, they should have annihilated each other, leaving only radiation behind. The fact that we exist in a matter-dominated universe suggests that some unknown process tipped the balance, favoring matter over antimatter. This imbalance is one of the great mysteries in cosmology and particle physics, and resolving it could provide crucial insights into the origins of the universe. Scientists study antimatter particles in high-energy environments like particle accelerators to understand why the universe favors matter. The Large Hadron Collider, LHC, at CERN is one of the primary facilities where particles are accelerated to near light speed and then collided to create both matter and antimatter. By examining these high-energy collisions, researchers hope to identify subtle differences in the behavior of matter and antimatter that could explain the asymmetry. For instance, experiments have shown slight differences in the decay rates of certain particles and their antiparticles, a phenomenon known as charge parity, CP violation. While CP violation has been observed, it is not yet sufficient to explain the overwhelming dominance of matter in the universe, suggesting that unknown factors or forces are at play. Antimatter also has practical applications, particularly in medical imaging. Positron emission tomography, or PET scanning, uses positrons to create detailed images of the body's internal structures. In PET scans, the radioactive substance that emits positrons is introduced into the body. When these positrons encounter electrons, they annihilate, producing gamma rays that can be detected and used to generate images. This technology has revolutionized fields like oncology and neurology, enabling doctors to detect cancers, map brain activity, and diagnose a range of conditions with high precision. Another fascinating application of antimatter is its potential use as an energy source or even as a propellant for spacecraft. When matter and antimatter annihilate, they release energy according to Einstein's famous equation, E equals mc squared backslash, making it one of the most efficient energy sources theoretically possible. Just 1 gram of antimatter would produce as much energy as several nuclear bombs. However, producing and storing antimatter is extremely challenging. Currently, only minuscule amounts of antimatter can be created, and the energy required to produce it far exceeds the energy output. Storing antimatter is equally difficult, as it must be kept isolated from matter in magnetic or electric traps to prevent premature annihilation. The possibility of using antimatter as a propulsion system for interstellar travel has been a subject of science fiction as well as serious scientific inquiry. An antimatter-based rocket could theoretically achieve speeds far beyond current chemical or even nuclear propulsion, potentially reaching a significant fraction of the speed of light. Such a propulsion system could reduce travel times to nearby stars from tens of thousands of years to mere decades, opening up the possibility of human exploration of other star systems. However, the technological hurdles, particularly in antimatter production and containment, make this a distant goal. In recent years, antihydrogen, the antimatter counterpart of hydrogen, has been produced and studied in laboratory settings. Antihydrogen is composed of a positron orbiting an antiproton, mirroring the structure of regular hydrogen. At facilities like CERN's antiproton decelerator, scientists have successfully created and trapped antihydrogen atoms for extended periods, allowing them to study the properties of antimatter in more detail. One key question is whether antihydrogen behaves identically to hydrogen, particularly in terms of how it interacts with gravity. Does antimatter fall down or up in a gravitational field? While all evidence suggests it falls downwards like ordinary matter, testing this experimentally could reveal new insights into gravity and the symmetry of nature. Antimatter is also central to certain cosmological theories and models. Some hypotheses suggest that large regions of the universe might be dominated by antimatter, forming antimatter galaxies or even entire antimatter clusters. If these regions exist, they would be separated from matter-dominated regions to prevent annihilation on a massive scale. However, no direct evidence for antimatter-dominated galaxies has been found, as these galaxies would emit light in the same way as matter galaxies, making them difficult to distinguish through conventional astronomical observations. The study of antimatter also has implications for theoretical physics, particularly in the quest to unify quantum mechanics with general relativity. In some models of quantum gravity, antimatter may interact differently with the fabric of space-time compared to matter. These models predict that antimatter might have unique gravitational properties, possibly leading to observable effects in extreme environments, such as near black holes or in the early universe. Investigating these properties could yield insights into a theory of quantum gravity, a unified framework that has eluded physicists for decades. The creation of antimatter also raises philosophical and ethical questions. Given antimatter's destructive potential, its applications extend beyond energy and medicine to theoretical weaponry. An antimatter weapon, if it were feasible, would have devastating effects far exceeding those of traditional nuclear weapons. While current production methods make this purely hypothetical, the idea raises questions about the responsible use of advanced technology and the ethical implications of harnessing such powerful forces. Despite its exotic nature, antimatter has practical uses on Earth and potential applications that could one day revolutionize energy, space travel, and even our understanding of the universe. Antimatter research, however, is still in its infancy, constrained by the immense costs and technological challenges of producing and containing it. Advances in particle physics, quantum mechanics, and cosmology are gradually expanding our understanding, bringing us closer to answers about why the universe favors matter and what role antimatter might play in the broader cosmic tapestry. In the quest to understand antimatter, we not only explore the boundaries of physics, but also gain insights into the universe's most profound mysteries. The matter-antimatter asymmetry, if resolved, could reveal why there is something rather than nothing, explaining how a universe filled with galaxies, stars, and planets came to exist. Each breakthrough in antimatter research challenges us to reconsider our place in the cosmos, offering a deeper glimpse into the fundamental forces and particles that govern reality. Whether antimatter will become a practical tool or remains a theoretical curiosity, its study pushes the limits of human knowledge and imagination. The journey to understand antimatter is a journey into the heart of existence itself, revealing a universe that is as paradoxical as it is profound, where the tiniest particles hold clues to the grandest questions about life, matter, and the nature of everything we see around us. The exploration of neutron stars has opened a unique window into some of the universe's most extreme conditions. Neutron stars are the remnants of massive stars that exploded in supernovae, collapsing under their own gravity to form incredibly dense objects. These stellar remnants are so dense that a sugar cube-sized piece of neutron star material would weigh as much as a mountain on Earth. Neutron stars bridge the realms of stellar evolution, nuclear physics, and general relativity, embodying the extremes of physics in a way few other objects can. They provide insights into the nature of matter under extreme pressures, the behavior of magnetic fields at cosmic scales, and the intricate dance between gravity and quantum mechanics. Neutron stars form when stars between about 8 and 25 times the mass of the Sun reach the end of their life cycles. After exhausting their nuclear fuel, the core of such a star collapses under gravity, while the outer layers are ejected in a supernova explosion. In the core, electrons are forced to combine with protons to form neutrons, creating a compact object primarily composed of neutrons. These stars are incredibly small, typically only about 20 kilometers in diameter, yet they contain more mass than our Sun, resulting in a density unmatched by any other known object aside from black holes. The intense gravity of a neutron star means that space-time around it is heavily warped, leading to strong gravitational effects. Observing neutron stars offers a way to test Einstein's theory of general relativity under conditions that cannot be replicated on Earth. Gravitational waves detected from merging neutron stars provide further insights into these objects and serve as natural laboratories for studying the interactions between gravity and extreme states of matter. These mergers create powerful gravitational waves, which can be detected by observatories like LIGO and Virgo, allowing scientists to study the event's dynamics and properties. One of the most remarkable types of neutron stars is the pulsar. Pulsars are rapidly spinning neutron stars that emit beams of electromagnetic radiation from their magnetic poles. As the star rotates, these beams sweep across space like the light from a lighthouse, creating a pulsing effect when observed from Earth. Pulsars can spin at speeds of up to hundreds or even thousands of revolutions per second, and their rotation rates are highly stable, making them some of the most precise natural clocks in the universe. This stability allows scientists to use pulsars in tests of relativity, as their precise timing can reveal minute distortions in space-time caused by gravitational waves or nearby massive objects. Pulsars also come in several varieties. Millisecond pulsars, for example, rotate incredibly quickly, with some reaching nearly 1,000 rotations per second. These rapid spins are thought to result from a process called recycling, where the pulsar accretes material from a companion star, which spins it up to high speeds. Millisecond pulsars are especially valuable for studying gravitational waves and testing fundamental physics, as their high rotation rates provide exceptionally precise timing data. Another fascinating type of neutron star is the magnetar, a neutron star with an incredibly strong magnetic field, sometimes 1 trillion times stronger than Earth's. Magnetars can release intense bursts of X-rays and gamma rays, thought to be caused by starquakes or shifts in their magnetic fields. These magnetic fields are so powerful that they can distort atoms, alter the properties of quantum fields, and even generate surface temperatures hotter than the sun's. The intense magnetic activity of magnetars can sometimes produce radio bursts similar to fast radio bursts, FRBs, suggesting a possible link between magnetars and these mysterious cosmic signals. Neutron stars also raise intriguing questions about the nature of matter under extreme conditions. The intense pressure within a neutron star compresses matter to densities far beyond those found in atomic nuclei, creating what is sometimes called neutron-degenerate matter. In these conditions, atoms no longer exist in their usual form. Instead, neutrons are packed closely together in a way that challenges our understanding of particle physics. Some theoretical models suggest that deeper within a neutron star, even neutrons might break down into their constituent quarks, creating an exotic state of matter known as quark-gluon plasma. Understanding these states of matter could provide insights into the behavior of matter during the universe's first moments, just after the Big Bang. One of the great mysteries surrounding neutron stars is the maximum mass they can support before collapsing into a black hole. This limit, known as the Tolman-Oppenheimer-Fokoff (TOV) limit, depends on the properties of neutron-degenerate matter and other exotic states that might exist within the star. Observations of particularly massive neutron stars, some exceeding 2 solar masses, have provided valuable data for refining this limit. Knowing the maximum mass of a neutron star has implications for understanding stellar evolution, black hole formation, and the physics of ultradense matter. Neutron star collisions have also become a key area of research in recent years. When two neutron stars spiral toward each other and merge, they create a burst of gravitational waves and a bright, multi-wavelength event known as a kilonova. This process is incredibly powerful, and it is believed to be a primary source of many heavy elements, such as gold and platinum, found throughout the universe. The detection of gravitational waves from neutron star mergers, combined with the electromagnetic signals from kilonovae, has provided a new way to study nucleosynthesis, the creation of elements in the universe. Neutron star research is also tied to the study of dark matter. Some models propose that neutron stars might contain dark matter particles in their cores or capture dark matter over time, altering their mass and behavior. If this is the case, studying neutron stars could provide indirect evidence of dark matter interactions. Neutron stars are also used in searches for gravitational waves and pulsar timing arrays, tools that help detect gravitational waves from supermassive black hole mergers and potentially from other exotic sources that could shed light on the properties of dark matter and the nature of spacetime. Neutron stars are also connected to gamma-ray bursts, GRBs, some of the most energetic events in the universe. Short-duration gamma-ray bursts are believed to be produced by the merger of two neutron stars, or a neutron star, and a black hole. These events release enormous amounts of energy in a matter of seconds, creating jets of gamma radiation that can be observed across vast distances. By studying GRBs, scientists gain insights into neutron star mergers and the environment surrounding these extreme collisions. Observing neutron stars requires specialized instruments. X-ray and gamma-ray telescopes are essential for detecting emissions from pulsars and magnetars, as well as the high-energy radiation from neutron star collisions. Radio telescopes, like those in the Square Kilometer Array, SK, and Very Large Array, VLA, play a crucial role in detecting and timing pulsars, while gravitational wave detectors such as LIGO and Virgo capture signals from neutron star mergers. These observatories allow scientists to study neutron stars across the electromagnetic spectrum and through gravitational waves, revealing the multifaceted nature of these objects. The study of neutron stars also has theoretical implications for our understanding of fundamental physics. Neutron stars represent an extreme regime where gravity, quantum mechanics, and nuclear physics intersect. The extreme densities and magnetic fields within neutron stars challenge current theories, and understanding these objects may lead to breakthroughs in quantum gravity and nuclear physics. The potential for exotic states of matter, such as quark matter or even hypothetical strange matter, means that neutron stars could hold the answers to questions about the composition of the universe at the most fundamental levels. Despite the progress made in studying neutron stars, many mysteries remain. Understanding the internal structure of neutron stars, the nature of matter at nuclear densities, and the processes behind phenomena like pulsar emissions and magnetar outbursts are ongoing challenges. Neutron stars sit at the frontier of astrophysics and high-energy physics, inviting us to explore realms of nature that are still largely theoretical. Each observation and discovery not only adds to our knowledge of these objects, but also helps to refine our understanding of the universe's fundamental forces. In our quest to understand neutron stars, we are not only studying dead stars, but probing the very limits of matter, energy, and space. They remind us that the universe is far more complex than it appears, with hidden layers of physics waiting to be uncovered. Neutron stars are cosmic laboratories, revealing insights about the nature of reality, the life cycles of stars, and the fundamental laws that govern existence. As we continue to explore these enigmatic objects, neutron stars offer a gateway to some of the deepest mysteries in science, connecting us to the origins, evolution, and ultimate fate of the cosmos. The study of dark energy is one of the most profound and mysterious pursuits in modern cosmology, as it involves a force that appears to be driving the accelerated expansion of the universe. First detected in the late 1990s, dark energy remains largely enigmatic, yet it makes up roughly 68% of the universe's total energy content. This mysterious force challenges our understanding of gravity, the fabric of space-time, and the ultimate fate of the cosmos, as it seems to be pushing galaxies apart at an ever-increasing rate. The existence of dark energy was first inferred from observations of type Ia supernovae, powerful stellar explosions that serve as standard candles for measuring cosmic distances. By comparing the observed brightness of these supernovae in distant galaxies, scientists realized that the universe was expanding at an accelerating rate. This discovery was unexpected, as it was widely believed that gravity would slow down the universe's expansion over time. Instead, the data indicated that some unknown force was overcoming gravitational attraction, driving galaxies apart faster than ever. The leading explanation for dark energy comes from Einstein's cosmological constant, lambda, a term he introduced in his equations of general relativity. Originally, Einstein added this constant to allow for a static universe, which was the prevailing view at the time. However, he later abandoned it, calling it his biggest blunder, after Edwin Hubble discovered that the universe was expanding. When dark energy was discovered, the cosmological constant was reintroduced as a potential explanation, representing a constant energy density that fills space uniformly, causing an anti-gravitational effect that drives the expansion. According to this model, dark energy is an inherent property of space-time itself. As the universe expands, more space is created, and with it, more dark energy. This self-replicating effect results in a form of vacuum energy that fuels the acceleration of cosmic expansion. This interpretation, while conceptually straightforward, raises deep questions about the nature of space, energy, and the stability of the universe. If dark energy is truly a cosmological constant, then its properties would be uniform across space and time, affecting the universe's expansion in a predictable, unchanging way. However, not all theories about dark energy rely on the cosmological constant. Some models propose that dark energy might be a dynamic field, similar to a scalar field, that changes over time and across different regions of space. This field is sometimes called quintessence, and it would interact with matter and space-time in a way that evolves with the universe. Unlike the cosmological constant, which exerts a constant force, quintessence would vary in strength and might eventually weaken or even reverse. This model implies that the properties of dark energy are not fixed, suggesting that the expansion rate could change over time. Another intriguing theory links dark energy to modified gravity. Instead of introducing an unknown form of energy, these theories propose that general relativity might not fully describe gravity on cosmological scales. In modified gravity models, the behavior of gravity itself changes over large distances, potentially accounting for the observed acceleration. These theories include F, R, gravity, and MOND, modified Newtonian dynamics, both of which adjust the laws of gravity to account for phenomena like galaxy rotation curves and cosmic expansion. If true, modified gravity would imply that our understanding of gravity needs to be revised, and that dark energy may not be an independent entity, but rather a manifestation of the universe's inherent structure. The study of dark energy involves not only theoretical models, but also large-scale observational projects. Surveys like the Dark Energy Survey (DES) and Euclid mission are dedicated to mapping the distribution of galaxies and measuring the expansion rate across cosmic time. By observing the positions and redshifts of millions of galaxies, these surveys aim to track how the universe's expansion has changed, shedding light on the properties of dark energy. This research involves baryon acoustic oscillations, BAO, which are regular, periodic fluctuations in the density of visible baryonic matter caused by sound waves in the early universe. BAO measurements provide a cosmic ruler that helps scientists measure the expansion rate, offering valuable data on dark energy's influence over billions of years. Gravitational lensing is another tool for studying dark energy. As light from distant galaxies passes by massive objects like galaxy clusters, it is bent by the gravitational field, creating distorted or magnified images. By analyzing these lensing effects, astronomers can map the distribution of matter in the universe and gain insights into the role of dark energy. Weak gravitational lensing, a subtle form of this effect, is particularly valuable for probing dark energy because it reveals how matter is distributed on large scales and how cosmic structures have evolved over time. Observing these patterns helps scientists test whether the universe's expansion is best explained by a cosmological constant, quintessence, or modified gravity. Dark energy also has implications for the ultimate fate of the universe. If dark energy continues to drive the expansion at an accelerating rate, the universe may eventually reach a state known as the Big Freeze or heat death. In this scenario, galaxies, stars, and planets will drift further apart until galaxies can no longer interact. Over trillions of years, stars would eventually burn out, and the universe would become a cold, dark expanse of isolated particles. Alternatively, if dark energy is dynamic and its effects diminish over time, gravity could eventually overcome the expansion, leading to a big crunch, where the universe collapses back into a dense, hot state. Some theorists even propose a big rip, where dark energy becomes increasingly powerful, tearing apart galaxies, stars, planets, and even atoms as the universe ends in a catastrophic expansion. One of the major questions in dark energy research is the apparent fine-tuning problem. The observed value of dark energy is extraordinarily small compared to the predictions of quantum field theory, which suggests that the vacuum energy should be vastly higher. This discrepancy is known as the cosmological constant problem, and it highlights a significant gap between our theories of particle physics and cosmology. Some physicists propose that the answer might lie in the anthropic principle, which suggests that we observe a universe with a low value of dark energy because it allows galaxies, stars, and life to exist. If the value of dark energy were significantly different, the universe might expand too quickly or too slowly for structures like galaxies to form. Dark energy research has also sparked interest in the multiverse theory. Some physicists speculate that our universe might be one of many, each with its own set of physical constants. In a multiverse, dark energy might vary from one universe to another, with some universes having much higher or lower values. The fact that we live in a universe with a low level of dark energy could then be seen as a selection effect. Only in a universe with such properties could observers like us exist. While highly speculative, the multiverse concept provides a potential framework for explaining the fine-tuning of dark energy and other constants of nature. Recent technological advancements are expected to provide new insights into dark energy. The James Webb Space Telescope, JWST, Nancy Grace Roman Space Telescope, and Verisey Rubin Observatory will allow astronomers to observe the expansion of the universe and map cosmic structures with unprecedented precision. JWST, for example, can observe distant galaxies and quasars, which serve as markers for measuring cosmic expansion at different points in time. These observations will help refine our understanding of how dark energy behaves across cosmic history, potentially shedding light on whether it is a cosmological constant or a dynamic field. Dark energy remains one of the most profound mysteries in science, challenging our understanding of the universe's fundamental nature. Whether it is an inherent property of space, a dynamic field, or an indication that gravity operates differently on cosmic scales, dark energy pushes the boundaries of physics and invites us to rethink concepts that have long seemed fundamental. Each discovery about dark energy brings us closer to understanding the universe's fate, as well as the forces and particles that govern it. As scientists continue to explore dark energy, they are not only seeking answers about the cosmos, but also about our own existence. The study of dark energy touches on the origins, structure, and destiny of the universe, connecting us to the vast, unseen forces that shape reality itself. In the search for dark energy, we confront questions that blend cosmology, quantum mechanics, and philosophy, reminding us that the universe is still filled with mysteries waiting to be unveiled, each one carrying profound implications for the story of existence. If you liked the video, then consider clicking on the recommendation and watch our other videos. Be sure to subscribe and see you on our next interstellar trip.